Check, check. Check one. Check, check.
Sound check. This is a sound check.
Check, check. One. If people can please start getting seated so we can get started in the next 5 minutes. Please get seated. All right, 9 a.m. sharp. It isn't, but we're getting started. So for our first talk of the day, we'll have Storm, who will talk to us about the data ecosystem Safari. If people would like be so kind to sit, we can close the doors so that we can get started. And also, to my right over here, you see Caitlin. Caitlin, raise your hand. Yeah, so Caitlin instead will be emceeing with us today. We work together in the investing and research team. And yeah, Caitlin will be our host for today. So a round of applause for Caitlin. All right, Storm, you want to take it away?
I don't need that. Mic check, mic check. Okay. Good morning, everyone. So since last year's conference, I've been working on a bunch of crypto data tools, and all of these tools share a common goal. We want to create modular Legos that we can assemble into new infrastructure and new applications. So today, I want to give you a tour of these tools and show you how they fit into the broader crypto ecosystem. So the flow of data in crypto is a lot like a food web. Food webs in biology are a way to visualize how energy flows through an ecosystem. So at the bottom, you have the energy source, the plants, and then you have animals that eat the plants, and then you have many layers of animals that eat other animals. This parallels the way that data flows through tools in the crypto ecosystem. So at the very bottom, you have the raw blockchain data source, the RPC nodes, and then you have tools that consume that data and process it and share it with other tools using APIs. And then at the very top, we have the interpretation layer where charts and tables and dashboards make the data consumable by humans. So this is the state of the world today. It's not bad, but we want this ecosystem to always be improving and evolving so that the way we use data gets better and better over time. One of the most effective ways to put evolutionary pressure on this ecosystem is by building new open source tools that improve the flow of data. So either allowing data to flow more efficiently or allowing it to flow in new ways. And so this is something I've been trying to do with these 4 tools. Each of these fits into a different part of the ecosystem, and I'm going to tell you a little bit about each one. And I don't have time to go into the full details, so I'll just sort of give the highlights and do a few tech demos. So starting with Mesc. Mesc is a way for all of your different dev tools to keep track of all of your RPC endpoints, kind of like an address book. So imagine you need to work with these different blockchains on the left, and you need to connect them to some of your dev tools on the right. The good news is all of these chains and all of these tools speak the same API, which is JSON RPC. But the bad news is this is a configuration nightmare. Almost every single one of these tools has its own unique conventions for how to configure its endpoints. This isn't really that big of a deal if you just have 1 or 2 networks, but if you have a lot of networks or a lot of tools, this becomes a very fragile and time-consuming problem. You have to configure each tool individually, and you have to keep those configs synchronized over time as you add or remove endpoints. Mesc simplifies this problem by creating a single source of truth. It tracks all of the endpoints, or all of your endpoints, and then it exposes that info to all of the tools on your system when they need to perform RPC requests. And standardizing the config like this lowers the operational complexity and removes a lot of potential for human error. So let me show you how this works in practice. Yes. So on my laptop right now, I use Mesc to track 27 RPC endpoints from 10 different networks. And so on the command line, I can do Mesc ls to list out these endpoints. And for each one, it tells me the name of the endpoint, the network, and the URL. Beyond the command line, Mesc also has libraries for Rust, for Python, and for other programming languages, so that this info is accessible in basically any environment. Mesc can track a lot of different metadata. So one example is network defaults. What is the default endpoint that you want to use for each network? So on the command line, I can do Mesc URL Ethereum, and it shows me the URL of my default Ethereum endpoint. I could do Mesc URL base or any other network, shows me the default endpoint URL for that network. Mesc has a few options for how to actually store this data, but in its most basic form, it's just storing everything in a JSON file on your computer. You can create one of these Mesc configs either by copying from a template in the Mesc repo, or you can do Mesc setup on the command line, and there's this interactive UI for creating and modifying your Mesc config. So to demo this, let me just delete my current Mesc config. If I do Mesc ls, config missing, all of them are gone. So let's do Mesc setup. Config file does not exist. Do you want to create one? Yes. What do you want to do? Let's add an endpoint. And we'll just use the classic 8545. That's where I'm running a base node right now. And you can see that it pings the node, it detects the chain ID, and it's ready to add it to the config. So let's name it local base, exit and save changes. Now when we do Mesc ls, the endpoint is there, and the endpoint is now usable by any tool that's powered by Mesc. So let me just restore my old config. And they're all back. OK, so beyond just tracking the endpoints, Mesc also tries to make it easy to manage these endpoints. And it has a lot of features for this. So if I do Mesc ping, it will ping all my different endpoints, check their latency, and also check their current block number. It can ping a lot of other information, like if you do Mesc ping client, it will check which client each of these different endpoints is running. It'll also show at the bottom if any of the endpoints are non-responsive. So Mesc is still a work in progress, but the overall goal here is to reduce the operational burden by standardizing the config process across tools. OK, so the next thing I want to go over is Cryo. Cryo is a tool for collecting blockchain data sets. Cryo can take any type of information available over RPC and turn it into a simple, local, flat data set. So up here, I've listed the different types of data that Cryo can collect. It's anything from really simple stuff like blocks, transactions, all the way to more obscure things like JavaScript traces and opcode traces. And when a lot of this data comes raw out of an RPC node, it can be very nested, very messy. Cryo basically packages it nicely into flat tables that are easy for other tools to consume. Cryo also uses a lot of tricks to make this process fast. And this actually enables a new style of workflow where you can perform all of the data collection and analysis for an entire chain's history on a local machine using open source tools. It's kind of like having your own private BigQuery instance just running on your laptop. Cryo was released about a year ago, and from the beginning, we put a really big emphasis on making it modular and leaning into open standards like Parquet. And for these reasons, we've seen Cryo adopted by many different organizations so far. So this includes data platforms, security firms, news outlets, MEV teams, and lots of different on-chain protocols. So let me show you what Cryo looks like in practice. So the most basic usage of Cryo is just collecting a vanilla data set. So let's say we want to collect all the logs over some block range. We just do Cryo logs, and then let's collect from block 10 million and then 100,000 blocks after that. So Cryo will go through, it'll pull that data from the RPC node. Right now it's the local one on my laptop, and it will package all that data into a bunch of parquet files. The interface is really simple. If instead of logs we want to collect blocks, we just say Cryo blocks. It'll collect that over the same range. And so that collected 100,000 blocks in about 2.2 seconds. If you want to list out the different types of data sets Cryo can collect, you can do Cryo help data sets, lists all those out. If you want help about a particular data set, you can do Cryo help name of data set, so like logs. It will show the schema for that data set, and it will also show what parameters are possible for that data set. Cryo uses Mesc for its RPC configuration. So right now it's just collecting from my default Mesc endpoint, which is that local base node. But I can specify other endpoints in a few different ways. So the standard kind of thing that a lot of tools do is you do something like RPC and then give it a URL like that. Cryo can do that. But because we're using Mesc, we can also do things like just give a network name, like Ethereum or Base or whatever other network you have configured, and Mesc will resolve that into the appropriate URL based on what you've configured. Cryo is also idempotent. So let's say we want to collect over a longer block range, a longer lasting job. So let's say 1 million blocks instead of 100,000. It'll start the job, and I can kill it at any point in the middle and restart it without issue. And this is really helpful because Cryo will make sure that none of the files end up being corrupted at the end of the day. So you have a lot of flexibility for, like, if you need to break the extraction process up into multiple chunks, that's fine. And then if you try to queue up that job again, Cryo will detect, oh, that data's already collected. I don't need to recollect it unless you explicitly ask it to. Cryo has a lot of other options as well. You can list these with cryo-h. You can export as CSV. You can filter things. There's a lot you can do. And then finally, Cryo has a Python interface that's pretty useful. So if we're in a Python session, we do import Cryo. And we can do something like Cryo or df equals cryo.collect. The Python interface has all the same options as the CLI. And let's say we want to collect a very similar data set as before. It will collect that data from the RPC node, and it will put that into a Polars data frame, df, that we can now use with all the standard Python patterns. So this is just a super fast and easy way to load data in Python. So the next tool on the list is TBL, or table. TBL is a Swiss Army knife for reading and editing and managing Parquet datasets. So for those that don't know, Parquet is a file format for tabular data, kind of like a modern CSV. In many cases, Parquet can be a simpler and faster alternative to using an actual database. And for this reason, Parquet has become a very common way for people to store and share different data sets. So let's say you have a bunch of Parquet files, either from Cryo or from some other data source. You might find yourself wanting visibility into those files. Or you might want to make some quick edits to those files. But up until now, there hasn't really been a quick and easy way to do these things with Parquet. And that's why I built Table. Table makes it easy to look up info about the schema and the contents of your Parquet files, as well as make a lot of edits to them. So let's look at some examples of TBL in action. OK, so TBL can tell us a lot of info about that Cryo data we just collected. So if we do TBL ls, that will list out the Parquet files and also tell us a bunch of metadata aggregated over those files, like the total row count, the file count. Another thing we can do is look at how those files are structured. So we can do TBL schema, and it will list out the two different schemas that are present in these files, one for blocks and one for logs. And for each schema, each line here represents one column in the table. And you can see the column's name, its data type, and its storage size. And this can be really useful for just taking a peek at how your data is structured. Another thing Table can do is make some quick edits to those files. So let's start by just doing a little preview of the first couple rows. Let's look at the logs. OK, so that's a little preview. Let's imagine that we need to modify the last column, chain ID. We need to change it to a different chain ID, let's say like 55. We can just do set chain ID equals 55. It makes those changes. Maybe we also need to change the type from U64 to U32. We can do cast chain ID equals U32, and it makes those changes. Right now, it's just printing the result to the console, but TBL has a lot of options for how to actually output these results. So the most maybe basic version is we can just edit all of the different files in place. And we can do that by just doing -- in place. And do you want to continue? Yes. I haven't parallelized this part, but I will in the future. It's going through all those files, editing them. And now if we do the preview again, we can see that those edits are now persisting in the files. Another thing we can do as an output mode is merge the results from all these different files into a single new file. So if we do -- output file, test.parquet, do you want to continue? Yes. It will now output everything to this single file. It'll take a moment because it's not parallelized. And now this test.parquet is present in the directory. A final alternative to quickly open up these files is in a Python console. So if we do something like TBL base logs star --df, it will open up a Python session and load that data into a data frame that we can now just do all the standard Python patterns with. So this is just a very nice convenience for if you need to quickly mess around with some data in Python. So that's TBL. Everything I've shown here might seem really simple and trivial, and that's because it is. But up until this point, there wasn't really an easy way to do it. And this is important because if you can do these types of operations in 2 seconds instead of 20 seconds, it really does change your relationship to the data. And you end up interacting with it a lot more because the friction is gone. The final tool I want to talk about is LBL. And this is just a quick preview because LBL is still a work in progress. LBL is a tool for managing labeled data sets. Address labels are one of the biggest remaining challenges in open source crypto data. And managing these labels can get extremely complicated, especially if you're dealing with lots of chains or lots of different data sources. And there are some nice projects out there for standardizing address labels, like the Open Labels Initiative, but there's still a gap in tooling. How do we actually connect the label data to the other tools in the ecosystem? LBL is the first tool built specifically to manage labeled data sets. So for example, LBL will make it so that you can load any data set you want in just a single line of code, whether it's derived from on-chain data like ERC20s or Uniswap pools or Chainlink feeds, or whether it's from Dune and maybe you want to get Hildobby's sex data set. Or maybe it's your own private label source that you made yourself that you also want to manage with the same interface. And I'm not going to do a tech demo of this one just for time purposes, but check back in a couple months and we'll have some cool stuff here. So those are all the tools I wanted to cover today. Ultimately, we're trying to improve the way that we use data at every stage of the pipeline. And the common approach here is that we're really embracing modularity and we're embracing modern best practices, with the ultimate goal being that this gives us a very powerful set of Legos that we can assemble into the next generation of infrastructure and applications. So that's it. Come find me if you want to chat about any of these topics. And thanks for waking up early to make it.
Any questions for Storm? Yes, no statements, only questions.
Do you support this? Does TBL support S3 files? So, or it's just local?
That's on the roadmap. That's okay. A very big goal right now, but it's not there yet.
That would be useful.
How's Cryo so fast? How did it pull that many blocks that quickly? Is there some secret sauce that you can share with us?
The secret sauce is Rust. I made almost an identical tool in Python, and I did every trick in the book that Python has for multiprocessing, everything like that. It was still an order of magnitude slower than just doing everything in Rust. And this is sort of built on top of Tokyo's MPSC, multi-producer, single consumer type flow, where you just divide up all the tasks and then do each one in parallel with some like semaphore. But there's actually like even more room for optimization. I just haven't gotten around to it because it's been fast enough for a lot of my purposes. But yeah, it's very convenient. It'll basically push most nodes as far as the node can go, and Cryo isn't the bottleneck.
I have a question, and also we've been using Cryo effectively to generate benchmarks for Reth because it's just a realistic usage of how you'd expect people to use a tool, and that can give you numbers that are actually reliable versus having to define a benchmark. You just capture a workflow, and that's your benchmark. I have a question, Storm, where last year you walked us through how, okay, there's actually a very powerful open data stack out there waiting to be leveraged to basically commoditize a bunch of the things that the clouds give you, and you just gave us an overview of how this captures the data lifecycle of like a data engineer, data scientist. Where are we going from here? So what is the vision of this local first processing pipelines, and why, and where do you want to take things?
Yeah, so I mean, the most basic way to answer that question is the boring version, which is with all these sort of tools ready and available, it becomes very easy to replicate what's already been built that might be commercialized right now. Like if you wanted to build your own Etherscan or your own Dune or your own whatever, it's becoming more and more possible to assemble these off-the-shelf components into whatever your vision is. And then sort of more broadly, everybody needs data at some point. I listed a few of the people that are using Cryo right now, like security firms, news outlets, MEV teams. We want to make it so that people are empowered to basically get whatever data they want by just using these off-the-shelf components. The like really interesting answer of where is this going and like what is the data endgame and what becomes possible now, that's basically like a big question box. We don't know yet. Basically, we're creating a bunch of potential energy, and we don't know how that potential energy will be released, but it's building, 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 and people being creative in the space and sort of like having their own vision, basically using these components to build better and better foundations for the actual thing they want to build. I think that's probably the most exciting thing.
Question. Is it possible to use Cryo as an indexing service? Like live pulling blocks that was newly created?
Yeah, so the ergonomics on that, there's still a little bit of improvement we can do, but it can basically do that. So Cryo has some settings for dealing with reorgs, and like if you want to create a reorg delay or you want to include certain information that makes it easy to process the reorg, we have that. One feature that we really want that we don't have yet is just completely seamless handling of reorgs, so that you can do like a more streaming type situation. But like Cryo, for example, can do like individual blocks really easily, really fast if you want to just like stay at the very tip, or it can do a delay like don't collect anything from the latest like 100 blocks because I don't want to deal with reorgs. You can also do that.
Thanks for the presentation. Are there any aspects of using Parquet to do this that are more complicated in the long run than a relational database, or more annoying, or anything along those lines?
Yeah, there are a few. One thing is that the indexing capability in Parquet is not as powerful as something like Postgres. So if you have something where you need to perform simple like range queries along one dimension, Parquet can be really good for that. You can sort of like structure your file from the ground up to support that specific query. But if you need to do something like I don't know what all my queries are going to be, I need to query by like 3 different fields all at the same time, filtering those, making it efficient, making it scale to billions of rows, then Parquet is probably not the best solution. Great. Thank you.
Hey, everyone. Well, thanks, everyone, for coming. So today, I'll share the progress that has been made in Foundry over the last 2 years, and I'll highlight some of the most impactful features that have been added that you may not have been familiar with yet. So what is Foundry? Foundry is a smart contract development toolchain. It's written in Rust. It manages your dependencies, it compiles your project, it runs tests, it deploys, and lets you interact with the chain from the command line and using scripts, especially via Solidity. It consists of multiple binaries. So we have Forge. So Forge is the testing framework. It's meant for compiling your smart contract code. We have testing, unit test, fuzz test, invariant test. We have a debugger, scripts to manage your on-chain interactions and deployments, and the verifying of your smart contracts. Next we have Cost. Cost offers a way to interact with EVM smart contracts on chain, which is like sending transactions, decoding on chain interactions, creating and managing wallets, that sort of stuff. We have Anvil, which is like a local Ethereum node, especially for developers. And then we have Chisel, which is a REPL for Solidity. So Foundry currently has nightly releases. And so to make sure that you stay up to date, you should run Foundry up very often, like on a regular basis. So it has become a bit of a meme, but you can set your alias GM to Foundry up. And I run that on all my systems. So Foundry has been growing steadily over the last 2 years. Both in terms of individual contributors as well as adoption by developers. So we've seen a growth from like 1% adoption in 2022 to now really becoming the default choice for any serious project. So for many, this is the tool that they use on a daily basis. And for all their smart contract work, from like a first proof of concept to a final deployment on chain. And it's used by many smart contract developers, auditors, bug hunters, searchers, and like everything in between. So a really quick background on me. I previously worked as a smart contract developer. I used Foundry as my daily driver since like the early days when Foundry was still DevTools RS. And in April, I joined the core team full-time. But to put some numbers to it, Foundry has like 137,000 lines of code in Rust, excluding accompanying crates, which we did quite a bit, splitting out things from core and into individual crates. So since the last conference last year, we've grown from 292 to 420 contributors. We went from 6,000 stars to 8,000 stars. And Foundry has over 4,000 merged commits. So we've been doing a lot. So we're also seeing an increasing adoption by developers working on the major protocols that are pushing innovation across the space. This is one of them. But other names are like Optimism, Maker, Succinct, Symbiotic, Euler, Lido. They're all using this on the daily basis and as part of their core testing flow. So anytime a project makes it to production, I feel is a potential for these best practices that are learned in during the development and testing phase of these projects to be shared and ultimately be fed back into Foundry. Improving the developer experience for all and pushing the space forward. So building better products ultimately requires building better tooling. So let's move on and talk about the features. So as of now, Foundry has 411 individual cheat codes compared to the 7 that DevTools originally had. So cheat codes are the way Foundry enables you to do things in God mode. We have cheat codes for things like creating a wallet, deriving a key, and signing. We have support for this new signed compact, which allows you to have signatures that are 64 bytes instead of 65, which is useful for a lot of things. We have things like setting environment variables, EVM state, dumping and loading of that EVM state from disk, recording storage reads, recording logs, directly interacting with an RPC endpoint, which is also really quite useful. We have things like interacting with JSON files, TOML files, serializing, deserializing, broadcasting one or more transactions, including raw signed transactions. That's a quite new addition, but this can be quite useful for private transactions and other things. We have string manipulations, native assertions, certain things that, like, certain actions are performed, such as expect call, expect emit anonymous, expect save memory. So these are all things that to make sure that you're not violating your assumptions. Other than that, we have many other utilities, impersonating an address, creating or computing your create2 address, deploying a contract from an artifact, and random numbers, which is also quite a new and recent addition. Previously, you had to use FFI for things like this, but now it's available directly inside. Yeah, and to use these cheat codes, you use Forge STD. So we've added an entirely new way of adding cheat codes, and it's now really quite trivial. So I would like to walk you through the process of doing this. This is one of the reasons, by the way, why we have like 411 cheat codes now. So the first thing you do is define the interface of a function that you want to implement. So you define basically, you describe on a high level what the functionality in terms of parameters would be. In this case, start broadcast. Then you implement in the relevant section, in this case the cheat codes directory. And the nice part about this is that you implement the cheat code trait, and then you simply describe the functionality and implement the logic. The self here holds the arguments that you describe in the high-level interface, and then we have a cheats subcommand that basically does some generation. And after that, it's available in your Solidity. So it's really this simple and straightforward. So if you have any new ideas about cheat code functionality that you would like to see, it's that easy to add. So digging in now, we have forking. A lot of you are familiar with this. It's just something that I wanted to point out, is that previously people were using fork URL, passing this into the command. But we now have cheat codes available that can do this in a much better way. So right now we recommend using VM create fork in your test setup and VM select fork in the test body. It's especially useful when you're testing cross-chain interactions. And with it, you can fork at historical block numbers, or even at a specific transaction hash. And if a transaction hash is provided, it will roll the fork of the block until the point that the transaction was mined. It's because the prior transactions are determine the state of the transaction that you're executing, so that's relevant. And by using VM select fork, you are easily able to switch between the different EVM forks, allowing you to test this behavior. And alternatively, we have VM create select fork to just wrap this and do this in one cheat. Next, we have isolation mode. So by default, the individual transactions inside of tests and scripts are performed as if they were part of one transaction. So for most cases, this is actually preferable because the setup and teardown overhead of doing this otherwise is quite significant. So for some use cases, however, especially those related to accurately measuring of gas, another approach is required. So what isolate does is you execute all test and script level calls as if they were separate transactions. You initialize them with like an empty journal state. You're triggering in pre and post transactions and cleanups. So this allows us to actually include the call data, the base 21,000 gas, the clearing of the transient storage, correct handling of your self-destructs, et cetera, et cetera. And in this case, like the difference is 21,064, 21,000 from the base and 64 for calling the function. But yeah, an important point to note here is that like none of these values are hard-coded, and like it is actually correctly as you would expect it, executing things as individual transactions, and therefore it can be considered like authentic and related to the request. So when running Forge test with the gas report flag, the isolate flag is now enabled by default, and this solves the long-standing issue where gas reports were not accurately reported. So Foundry previously supported tracing of external calls, making it difficult to debug intermediary values, and especially things related to the internal jumps. And we now support the decoding of these internal jumps. This flag is now available in both cast run and Forge test. So let's look at an example of a transaction of an ERC20 token swap using the Uniswap's universal router. So with the first decode internal, with the decode internal flag enabled, we first execute the previous transactions from the block, again to bring it into a state where, bring it to the relevant state. Then the next point is fetching the verified contract source code of the contracts that are actually used in the trace, and then we compile them locally with their respective compilation settings. And as a comparison, this is without decode internal enabled. So it only describes the high-level calls. It doesn't give you this introspection. It's good, but we can do better. And this is with internal tracing enabled. As you can see, we have internal function calls, internal storage lookups, intermediate values. So this is extremely powerful when you're doing your debugging. So this functionality is not enabled by default due to the overhead involved, but now you have a tool that you can reach to when you do need this level of introspection. So we've made many performance improvements over the last year in Foundry. As a benchmark, I've taken Solidi, which is a popular library for optimized gas snippets by Vectorized, and ran its extensive unit and fuzz test suite against a version of Foundry from 1 year ago and from a recent release. And this is even like a naive kind of benchmark, but it shows a speed up of at least 2x, but more likely depending on your code base. So we have a new feature called fuzz fixtures, and fuzz fixtures can be defined when you want to make sure that your set of values that you're using as inputs for fuzzed parameters contain certain values, right? So to do so, you use the fixture prefix, on any variable or function. And when you define the fuzz parameter in the test function, you use the same name minus the fixture prefix. And by default, you include or by default, any values that you include that are included in this fixture are chosen 40% of the time, 10% of the time are edge case values, and 50% of the time are random values. But this helps you kind of guide your fuzzing. We now support the replaying of failures using the rerun command. It's available on Forge Test, meaning that upon encountering a fuzz failure or a failing invariant test, the fuzzer corpus is persisted to disk, and upon the next run, the corpus is used when replaying the first case. This greatly helps with the speeding up the iteration cycle during development. So when a failure is encountered in an invariant test, a process called shrinking is performed, and a failed invariant test can include many steps and conditions that aren't actually contributing to the failure case. In order to reduce the failure case to a minimal reproduction, you iteratively remove unrelated cases and remove unrelated cases from the failure case. So Foundry previously took an optimistic approach, but this was rewritten entirely from scratch. And the speed up is very impressive. And for you, this means that your minimal reproduction can be extremely small and generally allows you to iterate quickly, which is obviously crucial for your development process. So improvements like this make Foundry not just a developer tool, but also a security tool. So we've recently added the show progress flag to visualize the process of running your test more easily. So it shows your fuzz runs, it shows invariant test runs, but it also shows your shrinking runs upon encountering a failure. So this is a more So we have Forge clone address. Forge clone allows you to create a new Forge project by cloning the source code of an on-chain verified contract. It includes remappings, dependencies, and compiler settings used originally when the project was deployed. So by default, the Forge clone clones the contract from the Ethereum mainnet via Etherscan, and it's also possible to do this for other EVM-compatible blockchains that Foundry supports by specifying the chain ID. So we now have support for Viper, which is a contract-oriented Pythonic programming language that targets the EVM. It's used by projects like Yearn, Curve, but also libraries like SnackMate. So in the process of adding support for Viper, we've abstracted the way that we how can I explain this? Either way, so we've abstracted the way that we interact with the compilers, opening a way to support languages other than the EVM. So in the last year, we've migrated entirely from Ethers to Alloy. You can now run Forge bind with the Alloy flag to create Alloy-compatible Rust bindings. This works for both Solidity and Viper. So to wrap things up, we have a big thing that we're working towards, which is our first stable release. So in order to achieve this goal, we are focusing specifically on 4 areas. One of them is correctness, completeness, performance and stability. And this means that any tickets that come in or any new ideas that we have, we evaluate, okay, how does it fit according to these goals and along these areas. So after 1.0, instead of slowing down, we are actually going to accelerate. I'm particularly excited for 2 new updates that we're planning. One of them is Anvil and Reth, which is a rewrite of Anvil from scratch to build a new developer node on top of Reth. Then we have Forge Builder, which makes it very convenient to use Forge as a library using the builder pattern. So please scan the QR code if you are. It's linking to the milestone ticket, and subscribe to it if you want to stay up to date with our journey towards 1.0. Thank you. Happy to take any questions.
It's really cool to see all the performance improvements to Foundry. My question is, one of the slowest parts of Solidity development is often just waiting for the Solidity compiler, especially if you are in a situation where you have to turn on via IR. And I was curious, has the team thought about attempting to write a Solidity compiler in Rust or to do something like that, or is that just too hard?
It's something. It's definitely like one of the concerns, right? That we understand, and it's not something that that we can. We understand.
We've been playing with the idea of doing one. So I'm over here. We have a parser that's really fast. We haven't gotten the codegen part yet. It is very top of mind. If there are compiler experts in the group that want to help with that, we might have a position, but let us know.
Hey, can you speak to the Anvil rewrite? What are you excited about in particular?
Yeah, so Anvil currently it's basically a full node implementation on its own. And it was written largely prior to Reth. So right now we have Reth in place, and it will avoid a lot of duplicate code. So right now we have PRs open for handling full reorgs and enabling certain tracing kind of RPC steps and all that sort of things. People are adding that currently still onto Anvil. But hopefully, once we have like this Anvil and Reth, a lot of this will come out of the box, and we can really push further. And it also opens up this idea of a lot of things were added on top of each other throughout the years. It gives us an opportunity to kind of rethink the interface, and generally get a much more performant node implementation rather than things related to caching and all that. We get a lot of cool things out of the box, basically.
Okay, next up we have Alloy is ready for production from Yash.
Morning, everyone. Thank you for coming out on a Saturday. Today, I'm here to talk about and declaring that Alloy is ready for production. And thank you. Finally, for those who don't know, Alloy is a complete rewrite of our previous framework, Ethers-RS. Alloy enables new API improvements and features that weren't possible in Ethers before. And we needed to rewrite for a multi-chain world. When Ethers was developed, rollups were in their infancy. Let's say now they're in their adolescence. So that's what we've designed Alloy for. So let's get started. So Alloy is right off the gate already used by the best teams to develop state-of-the-art products, such as Reth, Foundry, the SP1 ZKVM, companies doing data, infra, MEV stuff, and also the fraud-proof implementation by Optimism, Kona. One thing to note there is they have a no standard implementation, no STD, and Alloy is still capable because certain crates in Alloy, like the EIPs and the consensus types, are no standard. It does not make sense for us to make a networking related, like provider and transport, no standard, obviously. So in this talk, I'll mostly go through an overview and highlight the most powerful features of Alloy. Now, when Ethers was written, it was probably state of the art, and it was the best thing out there to interact with EVM blockchains in Rust. But times have changed, and so we're introducing Alloy, and the first low-level building block of Alloy is the primitives, which are great and powerful. You can also write Solidity in Rust now with the Sol macro. And to prepare for a multi-chain world, we're introducing a network types abstraction, which enables you to interact with multiple chains easily. And lastly, to override provider behavior, modify RPC requests and responses. Previously, you had Ethers middleware. The DevX with that was cumbersome. I'll talk more about that later in the slides, but we've introduced a new way to do the same and achieve better results in an easier way using what we call layers and fillers. So, yeah. So, right into Alloy primitives. Firstly, we've re-exported Ruin's U256, which is the big int for handling Solidity U256 types. And it has all the features starting from exponential powers, math ops, bitwise operations, even Boolean comparisons, and converting them to Rust primitive types. That might make you lose some precision, but it's definitely better if you want to print some big ints or display them elsewhere. So we have a type called fixed bytes in the Alloy core crate, and that essentially is the fundamental unit of representing byte arrays in the EVM now, in Revim, in Reth, etc. And the way that it works is it's generic over the length of the byte, and you can, so the foremost example, let's say, is the address type from the Alloy crate, which essentially is fixed bytes with a length of 20 bytes under the hood. And you can see that Alice, the address of Alice, is actually equal to fixed bytes. So now you can create your own named fixed types like we did for address. We even wrote a macro for it. It's called wrap fixed bytes, where you just pass in the named type that you want separated to avoid type confusion. And sorry. Yep. Up. So a little bit diving into the wrap fixed bytes macro. So the problem you face while developing in EVM land is that a lot of these things are represented by hashes, sometimes of the same length, sometimes of the different length. And the most common is the 32-byte hash. Now, it can be, the Kachak output is also 32 bytes. The Merkle tree item is also 32 bytes. Now, if you're using only fixed bytes to represent both of them, best case, you can have error-prone software, some incorrect logic while decoding stuff, and worst case, your program panics. So to do that, you can use the wrap fixed bytes to name and differentiate the fixed byte types. So what we're doing here is essentially creating a Kachak output and a Merkle tree item, and you can differentiate them while you're writing code. Well, into the meat stuff now. Alloy Sol macro. This lets you write Solidity in Rust. It's a complete overhaul of the Ethers ABI gen macro, which would only allow you to point to ABI JSON files or write ABI string representations and then create bindings for them. How we accomplish this is essentially because of the Alloy sol types, compile type bindings, and the sol type traits. So, and we also use the natively written, it's part of the Alloy code, the syntax solidity parser. And it's currently used by ForgeBind. Tim presented in the Foundry presentation that you can use the Alloy flag to generate Rust bindings for Alloy. So the Solidity macro essentially allows you to interact and deploy contracts very intuitively. So we've completely rethought how you should be interacting with Solidity contracts. When you're writing, the best programming comes out when you're interacting with a system that has a different VM and a different language, but communicating with that system feels native. So to do that, we have the RPC and the bytecode attributes in the Sol macro, which essentially let you create bindings and communicate with the on-chain contract. It can also let you deploy contracts if you specify the init code in the bytecode attribute. How does it do this? It uses the call builder type, which essentially is a wrapper around the ETH call and ETH send transaction RPC. And it takes care of all the ABI encoding when you're passing it args and sending your transaction or your ETH call. And it also decodes the return values so that the developing experience is intuitive and easy to use. Similarly, we have the event subscription. Without setting up filters for listening to logs or events, you can essentially just use the Sol macro, pass your event in Solidity, and create a filter for it. It also provides you with the subscribe method for subscribing to a stream, and also you can use a watch method in case you want to poll the endpoint and not subscribe. It obviously uses the ETH subscribe RPC under the hood, and again, ABI encodes and decodes the logs. So what you can see there, you have a decoded add log and the raw log itself, making it easy to interpret. So now, in October 2020, Vitalik wrote an article on the ETH Magicians Forum, what would a rollup-centric world look like. At the time, Optimism, Arbitrum were in their infancy. They were active on test nets, and we didn't have the reality what we have right now, which is we have n number of rollups with companies like Conduit enabling us to deploy different stacks, L2s, L3s, etc. While it looks like a very vibrant ecosystem from the outside for users with billions in DeFi, TVL, and Farcaster, decentralized social, and everything, it can be a difficult experience for developers since all these stacks and networks have n different transaction types, receipts, and network-specific implementation. So what it actually looks like is this. This is actually code from Ethers RS, which is using different network implementation and transaction type and gating them behind the Optimism flag. For example, the Optimism deposit transaction, which has a deposit nonce field, which if you would use natively to deserialize without actually, by just the vanilla implementation in Ethers, it would crash your program. And similarly, we had to write shallow middleware in Ethers. This is actually, you don't get to roast your boss's code everywhere. So, yeah. And so people ask, can devs do something? And we did something. It's called the Alloy network trait, which essentially unifies and the consensus and the RPC types of different networks and making the Alloy library ready for a multi-chain, multi-rollup world. The network state essentially defines the shape of the network. So it lets you implement a type-safe network representation. For example, this is the network representation for optimism. The only difference from the vanilla representation of Ethereum is the OP transaction receipt and the OP receipt envelope, which essentially contains the extra field deposit nonce. And so now you don't have CERD crashes anymore. You don't need to have CFG feature flags and different compilation configurations, etc. You can capture the network-specific nuances, such as the deposit nonce, L1 block number, gas use or L1, all into one and easy abstraction. But in case you don't want to write your own network implementation and you're not familiar with the network, but you still want to get started developing, what you can use is the any network type, which we already have in Alloy network. It essentially serves as a catch-all for all network variations, and it will consume all the extra fields that Optimism, Arbitrum, or any other network has, and CERD flatten it and put it into the other field. How does it do that? It leverages a type called with other fields, which is generic over the transaction type. The inner field is the transaction itself, and any other extra fields in that network's transactions are passed to the other field. And you can easily write a small struct and just easily serialize or serialize after the network request. Now getting into the Alloy provider, which is probably the most used part in Ethers. You have to interact with the network, and especially now in a multi-chain world, you want the provider to be generic over the network you're interacting with. This would enable you to interact with not only one network, but 2 or 3 or even more networks at once in the same code base without feature flags. So here's an example of the provider builder, which is building 2 providers. One is Ethereum, which is the default provider in Alloy, and another provider for OP, which uses the Optimism network implementation, which I showcased previously from the OP Alloy crate. The provider builder enables you to build a root provider with different configurations, not only networks, but layers, fillers, which I'll talk about in the next few slides. You'll see the builder pattern in Alloy quite often. We think it is the most intuitive and safe way for an amateur developer to get started and build a provider. So Ether's middleware. It's a thing of the past. It used to help you modify behavior of the provider and your transport. So every time you wanted to sign a transaction and send it to the network, you'd write a Ether's middleware. Every time you want to send a Flashbots bundle, write Ether's middleware. Caching, gas escalation, you name it, you need to write Ether's middleware. This approach was great at the time, but it's also too error-prone, and it has cumbersome DevX, and it needed a rethink. Introducing Alloy layers and fillers completely overhauls the Ether's middleware framework, but achieving the same results in a better and easier way. We build upon the tower-like layer and service architecture, where you can stack up multiple services. By the way, Tower is a networking library, if people don't know, that allows you to stack multiple services like retry layer, rate limit layer, concurrency layer. So we've built upon the similar principles of Tower and essentially separated the layers that you want to build, custom layers that you want to write, into their own use cases and buckets. So there are the mental model, how you should think about this is essentially 3 buckets. So if you want to write a layer that's independent of the RPC method you're calling, that essentially you want something like a retry layer or a rate limit layer, a cache all layer that caches all your responses, or just simply a logging layer which just logs the serialized requests and responses that you send and receive. So in order to do that, you'll write a transport layer implementation. We already have a retry backoff service layer inside Alloy that you can use that currently is used by Foundry to retry requests. And in case you want something more granular, in a case where you want to know you want RPC method awareness, where you want to know which method you're calling and how the response or the request should be structured accordingly. So you'll write a provider layer implementation for that. An example of that is a multi-data source layer. So let's imagine you want certain methods of the RPC to fetch directly from the network and certain methods to fetch the response from the cache if available. So you'd write a provider layer implementation that will let you do that and granularly override the provider trait and write the implementation for each RPC method you want. Now, if you want to override the transactional lifecycle, which basically means you want to set gas params, you want to manage nonces, sign transactions. So anything related to filling the transaction-related fields should be managed by the provider filler. More on that in the next few slides. So layers, again, like I said, it lets you modify and override behavior of the transport layer and provider. You can stack multiple layers on top of each other and have them work together at once. Fillers. So fillers manage the transactions lifecycle. It essentially enhances and provides a frictionless experience. For example, we have a method called with recommended fillers on the provider builder, which essentially implements a gas filler, a nonce filler, a chain ID filler, and in case you want to use a wallet filler, you can just do .wallet and pass your wallet to it. What will happen next is every time you send a transaction request, you never have to fill in the gas parameters, the nonce, the chain ID, or sign transactions manually. So what you see here on your left is the with recommended fillers flow, and on your right is the vanilla flow that you do without fillers. So you can see the difference in the lines of code. It's just 6 lines versus about 15, 20 lines. Yep. So what's next? So currently, due to the limitations of the provider trait, you cannot override and write your own provider trait implementation, such as wrapping it over RethDB. So we want to enable that. And to do that, we're introducing something called, in the next few weeks, we're introducing provider call, which will let you fetch data from multiple data sources at once. And this will allow you to wrap your provider trait over the RethDB or any other DB. And second is Alloy multi-call. We've had many requests to implement that. We've gone through the workflow. There are active issues over it, and hopefully we'll be implementing that also in the next few weeks. And lastly, the Alloy 1.0 milestone. So currently, even though Alloy is ready for production, we're rigorously improving it and finding new and different designs and architectures. So we essentially make breaking changes a few times or every few weeks. So we'd like to get to a place where it's completely stable and only new EIPs likely may or may not break Alloy. Yep, that's all. Thank you. Questions? All right. Thank you.
Next up, we have Tom from WebM talking about modern JS on Ethereum.
All right. Thanks for coming, everyone. Super excited to have the only JavaScript, TypeScript talk here today. So strap in. It's going to be a fun one. Usually when I give a talk, I like to go back and look at some historical things that went on, especially in Ethereum. Everything changes very quickly. And in the JavaScript world, there was this talk by Nozensmeister of Uniswap fame, where he was talking about like building apps at an ETH Global event in New York in 2019. And modern back then, according to him, which getting definitions from other people is always the move. You don't have to define stuff on your own. Yeah, dApps being like very responsive, feeling alive, like being, they're connected to blockchains, so having really good data and in your apps, making things feel up to date is really good for UX, really good for correctness. Like you click a button, you get a quick response, stuff like that. So that's kind of like the frame in which we're going to view everything we talk about today. And so the reason I decided to talk about modern JS stuff is we're getting close to the end of 2024. We're at like a conference that focuses on high performance bleeding edge software. So I was like, okay, what's bleeding edge today in the JavaScript world for Ethereum? And yeah, there's no better way than kind of taking a look at some history. I think the history of technology is really important. When we build tools, it's really nice to understand the context of where things have been in the past. It helps you measure progress between different iterations. And maybe most importantly, that someone said last night, if you don't respect your house, it will fall on you. So you can try to figure out who said that. But yeah, I just think it's really cool to look because a lot of the trends are the same. Like if we think about cars, it's like these are both like supercars at the time. The one on the top was like the best, but obviously no longer. But it still has a lot going for it. So yeah, a little disclaimer: this is not going to be comprehensive. I sort of like got involved, joined Ethereum in like late 2020. So a lot of the historical stuff, if it was still around by then, I like have used it. But a lot of the things that were, like 2014, 2015, like the back catalog, maybe some of you have experience with, but I unfortunately wasn't able to play around with that stuff directly at that time period. And yeah, if I missed something, super down to hear more about it. Probably not in the Q&A like I put down here because they have to be questions, not statements. But yeah, I would love to chat, learn more about everyone's experience. So yeah, let's turn back the clocks real quick before we jump forward into the present and talk about modern day. April 2015, Web3.js had its first major version. I'm sure a bunch of people have used Web3.js, whether it was in 2015 or more recently. Something that's really interesting with the context for Web3.js is that, while it was released 2015 April, the first commit was back in like September 2014, which is wild. Ethereum wasn't in production yet for mainnet. TypeScript, hadn't even had a first version yet. Like the first commit for TypeScript was like July 2014, if I'm remembering correctly. So like very different world that this project was started in, which is really interesting to see where it's come to today. I guess next on this tour is something called EtherSim. Has anyone used EtherSim back then? Or yeah, not super surprised. But EtherSim was really important because it kind of laid the groundwork for like a lot of future things. EtherSim was like a JSON RPC library you could use for testing or like in development, just kind of like test your changes in JavaScript. And this kind of evolved further, Truffle Suite came out of here, Ganache came out of here. So really cool that people were thinking about that, not too long after Ethereum launched there. And then, yeah, cut forward a couple years, Ethers.js, I think, was like a pretty big improvement on like the Web3.js of the time. And even if it wasn't, it was a different API, it was a different approach to problem solving, introduced things that were pretty interesting, like human readable ABIs and stuff like that. Performance was improved. And then on top of that, there was type chain, which, TypeScript has been around for a few years at this point, and there's like, a bunch of JavaScript developers are starting to realize that strong types are, pretty great. And so type chain made it a lot easier to then take your ABIs with your contracts and then spit out like a typed SDK, which then you can use to, call whatever functions or listen to events. And, it introduces like a degree of precision and correctness that didn't really exist in the JavaScript world before. And especially with Ethereum, it's kind of dangerous. You might pass like a value that is, a much larger value than you want for a number and transfer things incorrectly. Yeah, in 2018, maybe building on some of the things from EtherSim, Builder comes out. Has anyone used this before? Oh, nice, we got one person at least. Yeah, and this was, I think, pretty important improvement for developers. It was like, you could start building smart contracts and you didn't have to like compile stuff on your own. It was like a whole framework built in JavaScript, a precursor to Foundry in many ways. And Builder will like come back up here in a couple years down the line. Web3 Webpack is like our first foray maybe into like more front-end like app-specific related tools. If you're not familiar with Webpack, it's like a bundler for the web that allows you to like take some code, maybe it's like JavaScript or TypeScript or like some assets, SVGs, and then like spit out like a built bundle that maybe like transpiled the TypeScript to JavaScript or like minified the SVGs or some other stuff. And so Web3 Webpack was a way to like hook into Webpack projects at the time and have like an Ethereum provider you could use. And a lot of this, I guess the order of this, they came out around the same time, but EIP 1193 was really important along this journey because, it took like this chaos of like people shoving providers onto window.ethereum and kind of like standardized what an Ethereum provider API could look like, which then allows people to build a lot more cool things like Wallet Connect kind of like came out around the same time, which is again like I think a lot of people take it for granted today, but I take it for granted today because I wasn't around pre-Wallet Connect, but it allowed you to like bring mobile into the equation, and it was like a pretty big step forward. Wallet Connect widget now is called Web3 Modal, but this was kind of like the first attempt at a Connect Wallet modal, which like I think you start to see like people get more into like the UX side of crypto. Clevis and Dapparatus, has anyone ever heard of these tools? Yeah, you probably didn't because I made them up. I'm just kidding, I didn't, they're real. No, but these were like really cool tools. I wasn't aware of these until I went digging back through the history. Clevis was like a way to like run like a node and like do a bunch of like changes to that if you wanted to like go in and change like the gas limit or other type of stuff. And Dapparatus was like higher level components that you could use building like a React app or something. So Web3 Webpack becomes Web3 React. Noah Zinsmeister from earlier worked on Web3 Webpack, kind of formalized it more into Web3 React as like work on Uniswap, like the OG, or like one of the most well-known dApps was getting worked on. And Scaffold ETH is kind of like this iteration on Clevis and Dapparatus, which I think a lot of people, me included, like would get started with at like a hackathon or just like as a quick way to get building. Builder becomes hard hat, and so it's really interesting. You kind of see like initial versions of these tools get released because there was like a need. Someone needed this functionality to build. And then you kind of see them, like, a bunch of people use them because there was nothing that existed. They're a really good boon for productivity. And then you kind of see, like, maybe like a year or two later, like another iteration on top of them. You learn all the mistakes that you made in like the first version of the API. And hard hat, I think a lot of people got started on it. Works really well at the time for like forking networks and stuff like that. And so this is kind of like what the 2020 frontier looked like. Got a couple JavaScript libraries for doing lower level stuff, which is nice to have options. Maybe you don't like, how one thing does something or there's a bug. You can fork mainnet, which is really great for quick iteration and development. With type chain, you can code gen types and you get like all the benefits of TypeScript in that way. You can hook into React, which is important for building apps. You have like a connect wallet modal, so you can get started. You don't need to build that stuff from scratch. There's like a bunch of quick start stuff in the ecosystem where you can get really quickly started at a hackathon or prototype an idea, which is really valuable. And so this landscape is actually pretty incredible. Like there's ecosystems in crypto that don't have all these things today. So the fact that Ethereum had these in 2020, in these versions is pretty impressive. So I got involved in like 2020, late 2020, 2021 was building apps. And I think the big thing that was missing coming from like more of like a front-end world in like Web 2 stuff where there's like a bunch of great libraries and bindings for React and building user interfaces and stuff like that was something that was a little more stable. So worked on WAGMI just as a side project. Was wondering if there was some way to standardize and make things better. So it's a React hooks library. The most important thing for me was just having robust wallet connection. Using some other tools in the past for app development, it's like, maybe there'd be a bug where you'd switch networks and then it would just randomly disconnect you or stuff like that. And that just like wasn't a very good user experience. So yeah, it like supports all the usual suspects. You can also plug in to other, you can write your own connectors and plug in there. Back in 2022 also. The other thing too is there's just like a lot of duplication in code bases. I'm pretty sure most projects that got started like around this time would just go to Uniswap's code base, copy like all of the React hooks for like ENS related stuff, like sending transactions, signing, whatever, and just like pop them in their code base. So this like just tried to standardize like, all the features that you would want to do in your app. The other thing that was really nice, at least as an open source author, is like in the past, a lot of people would, for like more front end related libraries, would test, would like mock a bunch of the other dependencies for their tests. And so at this time, we started using hard hat forking for our tests. Eventually, we switched to Anvil, but this made it really easy to then reproduce issues and ship quickly without breaking things. So yeah, and then, once WAGMI was released, we started seeing like a bunch of these pop up. Rainbow Kit, which a bunch of people here probably have used or seen before, was probably one of the first libraries that built on top of WAGMI. This is like the new modern Web3 modal, but they had like another iteration on that. Now we have libraries that do like sophisticated, like account abstraction, smart contract wallet related stuff, which is pretty cool. Improving UX. There's like lots of these. It's probably one of the most interesting spaces to look at. I feel like a lot of them copy features from each other. A lot of people create new features that are interesting. So there's a lot of cool stuff there. So yeah, WAGMI was released, but it didn't really have any answer for type chain at the time. You could like use like WAGMI's hooks for reading from contracts, from like sending transactions, but you still had to like know what the inputs were for the contract that you'd be calling, and you could run into a situation where it like expects like a different value type, and you give it another one, and catching that at compile time was like an interesting idea, but didn't really know if it was possible. So worked on this library called ABI type, which powers all of like the type inference and safety in WAGMI and VM these days. And And it wasn't actually possible, before September 2022 because TypeScript released like this specific version like a month prior, which allowed you to do some more crazy stuff with the type system. But what ABI type does is really cool. It takes an ABI. It also works for EIP 712 type data. And it's able to, like, in the TypeScript type system, then infer, like function names, event names, which is helpful. Maybe you misspelled something, it catches that. It allows inferring different argument types, which is helpful because if you forget a certain value, it will kind of tell you and warn you ahead of time. Also responses, it will do that. And it is really robust. It works really well for even super complicated ABIs like deeply nested tuples that have like arrays with other tuples inside of them, and it can pull out the different names of the properties and stuff like that. It also does pretty wild stuff like say you have two functions that are overloads of each other, depending on like what parameters you pass in when you call the function, it's able to infer and narrow the return type. So yeah, this is just like really fun, low-level thing that powers a lot of the developer experience that we have. And so WAGMI was originally built on Ethers, which was great for getting started, but for the web, which is the context that WAGMI is used in, it kind of like demanded a little bit more out of the lower level library that it used. And so yeah, Ethers is a bunch of classes, which is fine. If you like classes, go for it. I think in the context of a modern web architecture that's tree shakeable and stuff like that, having a bunch of composable functions, which you're able to like remove if you're not using them in your code, was really good. So yeah, our main goal with VM was to like kind of like have an updated library that focuses on just like the building blocks that you need. You don't have to buy in to like a specific opinions or structure for things, how things work. Most of the functions in VM and the way it works is just how it was written in like EIPs and various specs. So yeah, this was like a big exercise in reducing bundle size to try to improve websites and like push developer experience further by adding like ABI type to a lower level library. It also does some other cool things, like has built-in multi-call support. No matter what chain you're on, if the chain supports multi-call 3, that works. Also, just some other optimizations, like it uses modern contracts that Web3 and Ethers didn't use, like ENS Universal Resolver, so it is able to resolve and look up with like one RPC call instead of 3 or 4, depending on what you're. I think the mic died. Test. Oh no, I guess it's back working. Sorry, I don't know what I did. Yeah, has like built-in Anvil support, works really well for that. So yeah, if you're using JavaScript and Anvil and you're trying to like set up some tests, maybe you're running end-to-end tests and you're using Anvil as like the back end for that. You can kind of like reset the network or do whatever via VM and Anvil. So yeah, kind of like what I've been working on until now is we released like the second major version of VM and WAGMI. WAGMI was like significantly reduced in scope, so it really just is like a thin reactive wrapper around VM now, plus support for all the different connectors, which makes things a lot easier. And a lot of cases, it's like the core of WAGMI that you want to use is like the wallet connection and account management stuff. And then if you need to eject to VM, it's like really easy to do some more custom low-level stuff. This was just something that we thought we should do, was add support for another framework. React is still by far the most popular one in crypto. There's a bunch of projects, especially in Asia, that use Vue.js instead of React, so we figured we'd add it and kind of extend out into different libraries. Probably at some point we'll add a Svelte-like adapter. There's a bunch of other frameworks that maybe we'll consider at some point, but I think Svelte is next on the roadmap. VM's chain type is really cool. I guess similar to the previous talk, Alloy, where it's talking about like the network types and how those kind of like determine the behavior of the library internally. VM is very similar. It's like the chain types are kind of like an inversion of control where they can define like their own custom rules for, you know, formatting a transaction, serializing it, whatever is specific to the network, and that allows us to not have a bunch of if statements inside of VM and custom code, which works really well. We released strongly typed errors for VM recently. In the TypeScript world, you don't really have strong error types. It can be anything. It can be thrown from wherever, and this is kind of like an attempt to try to wrangle some of that, especially when you're calling RPC methods. You might get some esoteric error from a node, and we've tried to wrangle that together to make it a little bit easier to either surface that error up to a user in like an understandable way, or be able to like, you know, handle it in some more controlled fashion yourself, like recovering from it, retrying, things like that. Another cool one that I don't think a lot of people know about is you can, you know, have your own deployless reads, either via bytecode, which I'll go over in a sec, or like a factory that's already deployed. Another really popular feature of VM is like this ability to extend VM into, you know, whatever other features you want. You can basically call client.extend, pass in, you know, some additional functions to be defined, some values, whatever else. And there's a few first-party VM extensions. We have one for account abstraction, which was released recently, the OP stack, which was a little while ago, and ZK Sync. And it's really cool. You can like build like full-on SDKs or other libraries basically on top of this. A lot of people have ones that, you know, use the internals of VM, but then expose whatever they have going on that's unique. We also have a bunch of experimental extensions under the VM/experimental entry point, which is just a good like proving ground to dump out a bunch of stuff that people might be interested in. So I would check that out. And yeah, I think kind of like what we're working on now and for the future is like making sure this stack works really well with the AlphaNet that some people have talked about over the last couple of days. And I think it's like an important component because if you know, features aren't in these JavaScript libraries, like they often aren't used by app developers. And so by connecting AlphaNet to, you know, apps with WAGMI or VM, hopefully it'll be an exciting like ecosystem where people are just trying a bunch of things out that, you know, you can send via URL to someone, they can test it out, as opposed to, you know, someone just being able to see something on the CLI or whatever. So yeah, where we are kind of like right now is we got a bunch of lower level libraries. I think, you know, there's a bunch of great things with Hardhat and Anvil where you can fork and build your dApps on top of that. I think we moved more towards like static types instead of code gen. It's just like easier to set up. It just works with TypeScript, which a lot of people are using. You don't have to run a separate CLI step. We have a few different, or a couple different front-end frameworks that you can plug into. WAGMI also works with Vanilla.js, so you're welcome to use it with anything else. We have like a bunch of Connect wallet modals. You can try out all of them. Since they're all built on WAGMI, it's like pretty easy to switch between them, just convenient. Got a bunch of quick starts and components. I feel like the hackathons these days, like people are able to move really quickly and get started just because the stack is like very obvious what you're going to use, how you're going to build things. And yeah, there's a few other things that I wanted to share. But first, like referencing back to this, like in order for things to feel alive and responsive and feel like you're connected, you know, one of the most important things is data, which is why I was interested to see Storm's talk earlier. And yeah, like apps need data, like to have good experiences. That's like the one bullet point on this slide. And there's a few different libraries out there that I think are interesting that approach this in different ways. That are, you know, some of them are more experimental than others. One of these libraries is called Tevum, a bunch of EVM plus letters. And yeah, Tevm's a really ambitious, cool project. It does a bunch of things. You can execute an EVM locally in the browser, which potentially is really cool. Just like XXs are really useful for plugging directly into like a node, so you don't have to worry about like network and serialization, deserialization. You know, potentially being able to like execute EVM locally in the browser, you know, doing simulations and stuff like that potentially speeds things up. And also with Node or Deno or Bun as well. I think one of the most interesting features is you can import Solidity directly into TypeScript. Why do you want to do this? I don't know, why not? I'll show you in a sec. And this enables something really cool, which I think the author of this library, Will, calls bring your own view function. So yeah, imagine that you want to read the balance of a specific owner of ERC 721. In VM right now, you do something that looks like this. Pretty straightforward. You get all the type safety and stuff. The downside of this is it's 2 RPC calls. You need to get the owner, and then once you have that owner, then you need to plug it in and get the balance. Not a huge deal, but you know, imagine if you're doing this a lot in your app, or if there's like multiple steps in between. So instead of 2 RPC calls, you need to do 10 because you need to resolve a bunch of stuff, and then like, you know, mash it together. And so doing this directly in JavaScript is more expensive in time. It costs RPC credits, all this stuff. And so what you can do instead with Tevm is you can write your own view function. This one's called a void, like the request waterfall, where you batch up all this stuff into like Solidity function, and then you're able to import that into your TypeScript project via Tevm. It does like some bundling and stuff behind the scenes. And then on the second to last line, which I guess you can't, that's a bummer. So, is there any way to move up the screen? Oh yeah. That's a good idea. Okay, anyway, what is missing there on the bottom is you're passing bytecode to the VM read contract function, and that bytecode is like the compiled bytecode from the balance of owner of functions. So then you're able to get all this stuff in one RPC call and do a bunch via like the deploy list reads and calls that VM has enabled, which is kind of cool. Another project that's interesting right now, I think, is Ponder. If you haven't heard of it, it's kind of like this all-in-one backend framework for crypto apps written in JavaScript on top of VM. And it has a pretty good developer experience. You really what you do is you set up your config file, and what you want to list here is any networks or contracts and stuff you're using. And you can create like a schema for it. These are like tables, which you know, either Postgres or SQLite, whatever, the data will be getting saved into for you to query later. And yeah, maybe not as fast as like a Rust CLI, but it's pretty fast. You can just like sync up and index a bunch of data, and then there's a couple options. Either you can query that data directly via API functions that they have set up, or you can just like listen to new events as they come through, and have some like custom logic. Maybe you send out like a notification to a different service. Here we're just saving it to like a database, which you can reference later. This is all just like, I think this is friend tech related stuff. Another project which is doing some pretty cool things in the similar vein to Ponder is Mud. Mud is a project that, you know, I think is like all about high performance applications, primarily used in like gaming and stuff like that. But a lot of these concepts can also like come in to what people are working on in their like normal apps. And because it uses like the entire like stack with VM and ABI type, you get like all the strongly typed stuff involved in there. One of the really cool pieces of it that's unique is real-time updates that you get. So similarly to Ponder, it's like you kind of define your table structure and set up you create some like methods to call into here. This is just for like a simple counter contract. And then you have a component where you can just like read directly from that value, and then it updates in real time behind the scenes with some of the infrastructure that they've built. And this is incredible because, you know, front-end developers and I think more JavaScript developers in Ethereum kind of like span like the gambit in terms of experience level. Like some of them are super knowledgeable about Ethereum. They've been in the space for a long time. They've used a lot of the tools that, you know, listed out before. And some of them are a little bit newer. They're interested in the space, but their like skill set is building user interfaces or something. And it's not really about like how to index data, how to query it, what the most efficient way, or like what RPC methods should I use. And this is really cool because you can get real-time updates from the chain just by, you know, calling a React component and having that set up. So yeah, that's kind of like how the landscape is laid out today. And yeah, I think we're in a pretty good spot right now, but going to keep pushing and see what else we can come up with. That's it. Any questions?
Hi, thanks for the talk. So you mentioned how like real-time data and responsiveness is important for the feel of these applications, and how VM's optimized for things like tree shaking to make the bundle faster. Have you looked at all at using like WebAssembly either for the core parts of VM or for porting Anvil for local simulations at all?
Yeah. Yeah, we've looked into that a little bit. Last year, I gave a talk that was kind of similar with like trying to bring in like Rust into the JavaScript world, and I think it's really promising. I haven't like checked back in on like what the current state of things is then, but that whole thought was like, the things that people use via TypeScript that's really valuable is the types. So it's like if you can write the types in TypeScript and then you can have the runtime be something else that's really fast, then you could potentially have like an incredible developer experience. Yeah, and I think combining those two things together is a little rough. And one of the biggest issues right now is that the bridge to Wasm, it like takes a decent amount of time. Also, when you're first like downloading the code in the browser, it can be a little heavier. And like usually a lot of the stuff that you're doing, maybe if you're executing stuff in the browser directly, you don't run into this, but a lot of the things with like JSON RPC calls and networking and stuff is the bottleneck anyway. So yeah, I think there's probably going to be some interesting stuff there soon, for sure.
Great talk, thank you. The Tevum example that you gave, the TEVM, the balance of owner of function, how is that different to a deploy list call, where like you would do an ETH call on chain with the with like a state override where that contract is deployed? Yeah.
I'm not 100% sure. Yeah, like how it would be different. That's a good question. Yeah, I need to look into that.
Or maybe it's just the same.
Yeah, I'm pretty sure it is. Yeah, because like you're just getting the bytecode, passing that in.
Yeah, but a better.
The difference probably is that you do the simulation locally versus on the node, right? Like when you do the ETH call with state override, the RPC must support state override, which some do not actually. And when you do it, you're actually running the compute on the server, whereas in the Tevum example, the EVM runs locally.
Okay, yeah.
So it's not doing an ETH call in the Tevum case.
Yeah. Okay, cool. Thank you.
Hi, great presentation. I was just wondering what your take was on how web development is sort of progressing with like more Rust frameworks. Like, I don't know if you had a chance to look at Rust frameworks, but if you had any like thoughts on that.
Yeah. I mean, it is interesting. There's definitely a lot of potential benefits for like performance-related stuff. Yeah, like I talked about it a little bit earlier. I think a lot of it is just around developer experience. It's not great right now because it's on the bleeding edge. It'd be hard for like most people to, build an app using something like that, but I think it's probably coming. Even just stuff like rendering the DOM faster, you can potentially speed up a lot by like using Rust.
How do you see the future of front-end development in the sense that is it going to be like fully powered by kind of indexers, or it's going to be like a mix of RPC and indexers, or just some maybe more powerful RPCs or something like this?
Yeah. I'm personally really excited about like potentially people being able to run their own nodes and indexers and stuff and make that more easy with like Reth and things like that on the horizon. Just because like I feel like most organizations, once they reach a certain scale for their apps, it's like really hard to rely on RPCs to get what you want, especially when there's like the trade-off with costs and whatever. So I think like yeah, the closer you can get things to like your own services seems to be pretty good. I think yeah, there's some like client stuff which could be cool that I don't think has been experimented with a lot in the browser. But yeah, I feel like a lot of these things is just like, you know, if you're interested, if you want to reach out to us and you want to like explore with us, we're happy to. But I think there's like so much opportunity just to like work on, you know, new projects on your own that push this stuff forward and then get it in front of people, because people want better solutions than just querying their RPC and mashing the data together. Sick.
Okay, next up we have Brian from Base talking about Reth benchmarking.
All right. All right. Thanks, everyone, for coming out on a Saturday. And I know we're getting close to lunch, so probably getting low on blood sugar and caffeine. So I'll try to take you through a nice, easy journey through benchmarking Reth. So don't need to tell all of you here, but we think that on-chain is the next online. And in order to sort of achieve that goal, we practically want to vertically scale Base to 1 gigagas a second. It's a phrase that you heard a lot yesterday, but not yet today. So where are we today? We're at 10 megagas a second. We've gone up 4 times this year so far. That's pretty good, but we still have another 100x to go. So why have we not done that yet? There's a lot of challenges along the way, which covered in detail yesterday. L1 data availability, fault-proof compatibility, state growth, but today I'm going to talk about the execution performance part of this. So it's important to recognize that, like, well, we're concerned the most about our scaling limits in the most adversarial conditions. So, like, what does the worst-case block or transaction pattern look like? And while we have a nice security model as a rollup of a 1 of n, it's only really useful if there's other people running nodes safely. So we want to make sure that we have like a pretty good template for all of our ecosystem partners in order to run a node safely that can stay up to sync from our snapshots. Okay, so let's see. So an Ethereum client has a ton of moving parts. There's a lot of different opcodes, over 100, that have fairly non-deterministic costs. There's block overhead in addition to the transactions themselves. Of course, computing the Merkle state, computing the tri-root. There's also the fact that the performance will probably degrade as the state grows and the database gets larger. And then also none of this is running in a vacuum. There's, of course, the underlying hardware, software, file system, and so forth. So how are we practically benchmarking Ethereum? Now, there's a lot of different transaction patterns and types, from sends, transfers of tokens, swaps, non-financial activities like gaming and social. And they all have very different access patterns. And you can't really statically analyze any of these because what a transaction does is entirely determined by the EVM state and not really what's in the payload. So one of my colleagues built this tool called the replayer. It's sort of a black box tool for running through a sequence of blocks and transactions, sort of playing the part of a consensus client. Can plug into an existing Ethereum node, pull down the block and transaction data, and then funnel it into a new node that you're running locally. So in addition to running through past transactions and replaying them, it can inject other additional transactions or tweak the payloads in various ways. And then record timing stats at each step of the way, and then perform tracing to get us the data we actually need to do our analysis. So that means looking at the opcodes executed and checking the storage diffs. So wanted to create a standard test environment here. We ran all these benchmarks in Reth 103, which I realize is a little bit behind the current version now. And this is the OP version, of course. And chose fairly commodity hardware that anyone can spin up today on EC2. So this is like the i3 EN6X large instance type, which has plenty of CPUs, lots of RAM. Most importantly, it has 2 locally mounted NVMe drives, which critically are mounted in a RAID 0 configuration on like ext4. So a very standard no frills file system. So now the other important part here is to look at the actual sample data. So we wanted to find block ranges that have a wide range of access patterns, specifically those which are very disk and storage intensive. Settled on like a 25,000 block range on base mainnet, starting roughly around the 11 million point. And this notably contains a very high concentration of Zen transactions. If you operate an EVM chain, you might be aware of this. Storm actually has a great blog post detailing sort of the impact of Zen on a variety of other EVM chains. But most importantly, this sends a ton of S loads, S stores, contract deploys, and sometimes self-destructs at the chain. Okay, so let's try. So running through these 25,000 block range on the given configuration, we can see this chart here where I took every data point, which corresponds with a single block, and charted like the number of gas in megagas on the x-axis, and the time in seconds to go through the full block execution and import process. So if you squint really hard, you can say, okay, cool, there's a linear equation here that generally maps to this and gets you around 60 megagas a second. But it's also obviously not a linear function here. We have the line towards the bottom. We have this cluster in the corners, the top left and top right quadrants. So this is actually very poor correlation between block gas and execution time. So obviously we need to go deeper. We can't just model this as like a linear function of just like how much time per gas. But also there's like a ton of different opcodes, as I mentioned earlier. It doesn't make sense to benchmark them independently. So intuitively, we know that like read and write ops are a lot less predictable from just like adding 2 numbers or multiplying off the stack. So what we did here is I grouped a lot of different operations into different buckets, like storage, ops, call ops, account reads, and so forth. And I sort of sliced the data a lot of different ways. And sort of the best thing we came up with was a fairly simple formula. So our variables here are like our total gas for the block, and the storage-related gas. That's S loads, S stores, calls, anything that really needs to possibly read or write from disk, and then like an assumed overhead per transaction. So running like a multivariate linear regression, like least squares, we were able to like create a cost function here. It's better, but it's so it kind of like tracks the bottom case here and the top corner, but it's missing what's really the most important, which is our low gas, high time blocks. So this is definitely not the right solution here. So it's important to step back and ask why is this the case. Gas is not really there to reflect execution time exactly. It's set up. Gas prices are set up for incentives structure. So while in Reth it might be computationally equivalent to add a new storage slot, update an existing one, or delete one, they all cost very different amounts. Now separately, there's other factors such as like failed transaction and inverted contract calls costing storage, but maybe not actually writing. And then finally, at the end of every block, we're only needing to calculate the state root changes based off the total net changes. So there's a lot of double counting depending on what transactions are in the block. So putting this all together, we can kind of reduce this to a few fairly simple variables. So we model like the total gas consumed, which critically recounts any refunded gas. Like just because some gas was returned to you for clearing out storage doesn't make it any cheaper in the short term. And then also excluding things like call data, which are there to keep the block small but don't really add any cost. And then we count the number of slots changed. So that's like the number of accounts changed as well as like storage slots within individual contracts. You put this all together on a block level, you get like a two-variable equation. It's very, very simple. And running the same regression pattern again, we actually get something that shockingly accurate in terms of modeling our various transaction patterns. So what this comes down to on this specific test example is like around 2 nanoseconds per gas, another just under a millisecond or per slot changed, with like a very small overhead per block. So it tells us a good number of things here. One, that like we can definitely have shorter block times because the cost of overhead is very low. And it also means, in practical terms, that updating and deleting storage slots is really the most expensive use of gas on our commodity hardware. So after you factor in refunds, it's only around 4,000 gas to delete versus like 22,000 to add a slot. So that's like a 5 to 6x difference in cost. So in the real worst case here, we're at like just under milliseconds per slot updated, which gives us just over 1,000 slots per second, which is in the absolute pathological short-term case is like just over 4 megagas a second. Now there's a lot of silver linings here, like every time the same storage slots accessed in the same block, those are additional ones are kind of like free for us. But okay, so now we did our benchmarking on like one specific configuration. It's important to like introduce a few other variables to see how that changes things. So the next really good news here, and I'm not sure how much you can see it, but throwing hardware at the problem does work. So we bumped up the instance size, still far below the max available on commodity cloud hardware, which doubling instance size on EC2 gives you generally twice the CPUs, twice the RAM, and twice the disks. And really all that matters here is twice the disks in RAID 0. If we look at sort of the bottom, I'm not sure if you can actually see the bottom line out in the audience, but it stays roughly the same. So Non-storage related execution stays very constant because there's really no parallelism. There's not much to do with other CPUs. But the IOPS more or less doubles. Time to perform storage operations halves. So that's great news. There's a lot of room to grow there. Now, also important to compare this against Geth. So we took the lightest configuration possible, which is full node, PathTB, and you get a much more linear representation of gas, which is actually kind of unsurprising when you think about the fact that Geth is the majority client on which all these gas prices were originally set. Now, there's a few caveats here. One is I ran this on a much smaller set of blocks because the traces were like an orders of magnitude slower, and I didn't really want to wait a week for this whole thing to go through. And the other important point here is that Geth is actually very rarely actually flushing the disk. So even though we were performing lots of storage writes, only twice did this self-report as actually flushing the changes to the disk. So that also means that we can't really explain the P95 spikes of this data set. It's all kind of shows up as noise and is not mapped to any particular pattern of opcodes or storage access. So just kind of an interesting takeaway here. So maybe you're running your own node and you've heard there's cool file systems out there that will let you have on-demand or live snapshotting and cool features like copy on write, like B-tree file system or Btrfs. Don't do it. If you look at this y-axis, we've gone up sort of a 10x multiple, a whole order of magnitude slower on the worst case. So just using file systems with smart features is really not a good way to run a database because your worst case performance just gets far, far, far worse. And in fact, we couldn't really model this either with a similar cost function analysis as before. So where does this really, so where are we today really in wrapping this up? So we know we can get around 500 storage writes per second per NVMe drive in RAID 0, which scales generally linearly. So in the absolute temporary adversarial case, when you're just deleting lots and lots and lots of slots and doing nothing else with your gas, that puts you down somewhere on the order of 2 megagas a second per drive, which also will slow down a bit as state grows. But the good news here is that all other gas is super cheap on Reth specifically. So we're seeing somewhere on the order of 500 megagas a second at current block sizes. And we know that there's a lot of things being done to get that even faster. And the other takeaway here is that Geth full node on PathTB generally has an average case that maps sort of to the middle case for Reth. So that was when you have storage heavy, but not pathologically optimized storage heavy access patterns, even though it's only rarely actually flushing the disk. So that tells us there's really good performance implications on Reth, and we've made it huge leaps forward here. So just looking ahead, we know there's plenty of levers available for improving execution speed. There's RevMC, a compiled EVM bytecode. We can run things in parallel and actually start to use all those extra disks or extra CPUs we have lying around idly. And really the biggest one we can have right now is optimizing our disk writes. That really is the critical path to scaling further right now, ignoring things like DA and other blockers along the way. So one takeaway here is that high throughput chains probably want to start charging more for storage access. And you can do this with just breaking EVM equivalents. You can just charge more. It's not something we want to do lightly because it's just not great for the developer experience. So there's probably a good reason to align on Vitalik's multi-dimensional EIP 1559. Set a number of storage slots you want to write per block and price it based on that. So thanks everyone for listening to my talk.
Thank you for your work. Amazing presentation. I wonder if you measured the difference in read and write for storage, and how does the RAM affect this? Because if you feed the whole database in memory, the writes kind of the same, but reads instant from memory. Yeah.
Yeah, great question. So I didn't want to bore everyone with lots and lots of slicing of the data, but I did specifically test that. So when we were bucketing storage slots by category, I was trying like read access versus write access, and it didn't actually matter too much. So like the earlier graph where we weren't looking at storage slots themselves, we didn't really get a much better model. And there's sort of an intuitive reason for that, in that you already are paying a lot more in gas for writes versus reads. So I think it's actually fairly accurate right there. Now, as for RAM, we did not try putting the entire state try in memory. I'm sure that would completely change the model here if you're no longer having IO-bound operations.
If you go back to the last diagram of RE's correlation between gas and estimation, yeah, this one. So there still seems to be a class of outliers on the upper left corner. Are they significant or only visually significant?
That's a good question. It was generally within the margin of error. Let's see. So it's probably not, modeled perfectly as a linear equation. As was sort of covered yesterday, the overall storage, or the overall try representation, is actually a try of tries. So when we update storage slots on contracts, those are rolling up into the overarching master try. So there is a somewhat nonlinear effect here. But this is generally a good enough approximation for figuring out our upper bound of scaling.
Oh, one more question. How many rounds do you guys did for this experiment?
So this specific test here is 25,000 blocks range. And I ran this, I want to say on the order of 5 or 6 times since I created this model.
Thank you.
I guess this is a question about the Reth design in general. So in order to account for the moving parts of Ethereum and the different chains, so we noticed there's a lot of dynamic trace objects being wrapped into a box, and and futures being pulled by Tokyo runtime. So I feel that would be an overhead contributing to the execution, because it compiles V tables instead of static jump in the binary. So I wonder getting rid of those things contribute to much lower performance overhead, independent of gas count, or depending on the gas count.
Okay, so that's a good question. Let's see. So I think we can definitely squeeze out more performance on the raw execution layer, which is sort of the low line here. I don't think that would necessarily impact sort of the worst case performance, which is kind of what we've been focused on in this test. Given that that's entirely bound by storage slot rights. If there's a great way to statically analyze the transaction and understand what's going to be written to in advance, then maybe we can really start to squeeze out additional performance there.
Hey, great presentation. I'm over here in the couch. So I was wondering, caching could probably help on some of this. So I was wondering if you had done any analysis on a specific cache solution that might work, because there are obviously different algorithms, and some of them are, for example, more temporal in nature. And I would imagine for on-chain activity, you would have lots of activity localized on some accounts, like Uniswap or Zen in this case? Thank you.
Yeah, so there's, I guess, explicit caching, and there's also sort of the implicit caching of like what happens within the context of an overall block. So if you have, if you were building the block and you could say, okay, I know there's a bunch of transactions that are going to go and use the same Uniswap contract, you kind of get that extra performance for free just by, charging the end user for the computation, but not really inducing any additional cost on the node. We can definitely access or improve the read performance across the board just by like proactively populating cache. I think it was the Rise team yesterday had like an interesting point about hinting. A node providing hints to other nodes about what transactions might. I think you can provide hints from like a sequencer to additional nodes about like what storage slots can be read. I know that's kind of like the idea behind the access lists, but they're not really well adopted. But this, we can definitely prefetch storage slots and put them in cache to improve the average case here.
Okay, we have time for one more question.
Thank you for the presentation. Do you think your findings are kind of a bear case for trying to price gas in a way that's a little bit too clever and kind of overfits the implementation? Like, for example, Get seems to be somewhat kind of, more aligned with the gas costs currently, while, Reth doesn't kind of fit the same way. Does that mean we should basically never try to fit that because somebody else might make a new client that it's not going to fit? And a second question is, have you done any benchmarks that are a bit more about consuming data from Reth? So for example, if you have like subscribers to WebSockets and whatnot, like trying to measure the latency, the things that may not be about increasing the gas limit, but more like the experience of using Reth.
Okay, so these tests were focused on block production execution, so don't have the benchmarks on like RBC subscriptions and that kind of latency. But okay, so as for your first question here, I think it's important to like ask as like a chain operator, like what are the clients you want to support, and what are sort of the price models here for each of them. Ultimately, you're trying to figure out like what can we squeeze in reasonably on either average or absolute worst case. I think at the end of the day, you will have clients that are running way faster than other clients and can just, whether that means they can do more optimized block building or serve other additional RPC requests like in between execution time. Like you're still going to be sort of bound by your worst case. But I think the other point here is like Reth is currently focused on like providing a very consistent fast access archive node, where we were sort of comparing that to the PathDB full node on Geth, which is really only able to serve like the current state at any point in time. So I think if we were to like sort of take some of those or apply some of those changes and only like buffer writes to disk and only periodically flush them, we'll see this compress and look much, much closer to the Geth side, just much faster.
And this specific thing we also have observed, and we have an experimental rewrite of the consensus to execution layer interface, which should help with that by removing the writes from the critical path. So this is not released yet. It's behind an engine.experimental flag, It's not recommended by any means for production use, but any people doing benchmarks should reach out to us for working with this.
Yeah, looking forward to rerunning these with those changes and really seeing the numbers go down.
Okay, so next up we have lunch. It's going to be similar to yesterday. It's just outside. We just asked that you be back here at 12:30. We have a bunch of stack talks about Reth examples out in the wild. Starting with Emily, CTO and co-founder of Shadow, who's going to be talking about Shadow Reth. And I will make the stage for her.
Hi, everyone. Hope you guys had a good lunch. I'm Emily. I'm one of the co-founders and CTO of Shadow, and I will be talking about Shadow Reth today. Oh. Sorry. Here? Okay. Okay, awesome. First, what are shadow logs? Shadow logs are gasless logs that can be permissionlessly added to an already deployed smart contract, and they get generated in an off-chain execution environment. So why are shadow logs cool? Shadow logs allow you to permissionlessly add as many custom logs as you want, all without increasing the gas burden to your users. And then this unlocks deeper data coverage, and you can get net new contract data, data that's like really hard or nearly impossible to get otherwise, or really cumbersome to get. You have to parse traces or do expensive ETH calls, things like that. And as a result, shadow logs can drastically simplify your downstream data pipelines. So, for example, say you wanted to build a new front-end feature, but your currently deployed contracts don't make that data easily accessible. Instead of redeploying your mainnet contracts, you can run a shadow contract that makes that data easily accessible. And we think all of this will allow people to build better, more data-rich products and services for their users. So if you wanted shadow logs, the steps are pretty simple. You first edit the source code of an existing smart contract to add your shadow logs. You then run a shadow node with your new shadow bytecode of your contract. And then the third step is you can get your shadow logs by querying the node. So at a high level, the way that this works is when a new block happens on mainnet, we instantly re-execute the same mainnet transactions from that block in an off-chain execution environment. And then this off-chain execution environment is super similar to mainnet execution, but instead of executing the mainnet contract bytecode, it swaps out the mainnet contract bytecode with your shadow contract bytecode at the addresses of your shadow contract. And then when your shadow contract gets executed, it reads from the same exact mainnet chain state, but is emitting all these additional event logs. And then you can fetch these shadow logs over JSON RPC, just like you can fetch mainnet logs. So this off-chain environment is shadowing mainnet, right? It's re-executing the same mainnet transactions against the same mainnet state, but can output like 10x or 100x more logs, all without increasing the gas burden of your users. So taking a step back, let's talk about what the job to be done is whenever you're building crypto data infrastructure. With any crypto data pipeline, you're generally doing these three things. You're extracting raw on-chain data by fetching data from a node. Then you transform that raw on-chain data into a decoded human-readable format, and then you load that transformed data into some data store that you can then use for analytics or for your front end or whatever you need. And this is no different than standard ETL pipelines, right? That you see in traditional large-scale data pipelines. So this is how most crypto data pipelines are architected today. The source of truth of all on-chain data are always nodes. And these nodes are built to quickly discover and execute those new blocks and then commit those new blocks and the state transitions to its own database. Then your data pipeline subscribes to new blocks that get added to mainnet. You can do this via WebSockets, ETH subscribe. You can do this in a polling loop. Either way, you do this over JSON RPC. And then when you get that new block notification, you go and then fetch all this additional data that you need, again, over JSON RPC. And oftentimes you have to fetch traces or make ETH call requests or do a lot of kind of heavy RPC endpoints. And this is the extract step. Then you write custom transformation logic to transform the data into your own use case. So you might do this in TypeScript or SQL or Python within a framework like subgraphs, for example. And this is your transform step. And then finally, you write all that transformed data into a data store like Postgres or Snowflake, and this is your load step. So there's some drawbacks to this architecture. The first is that the extract and transform steps can be really slow from a performance perspective. You have added network time if you're going over the network, and you're also paying a cost for JSON serialization, deserialization every time you fetch data from a node. And then as a developer writing these data pipelines, it's not really a great experience as well. You're generally stuck with the event data or the contract data that was originally deployed in the contract, and that contract could have been deployed like years ago. You also can't reuse any of this logic that is actually running on-chain in your transformation pipelines. You often have to rewrite the same logic that lives in smart contracts, but you rewrite it in like TypeScript or Python. And if you don't want to build an indexer from scratch, you can use frameworks that exist out there, but there's like some ramp-up cost of learning how those indexing frameworks work. You're working with YAML files, stuff that no one likes. So how does this change with Shadow? The idea behind Shadow is that you can actually co-locate the extract and transform steps. So you can write your transformation logic directly in smart contracts, run that transformation logic through the EVM, which has direct access to the exact chain state that you want, and then emit the transformed data as normal EVM logs. So this is still following the same ETL pattern, right? But instead of writing your transformation logic in SQL or TypeScript or Python, running that over JSON RPC, you can write your transformation logic in Solidity or Viper and run it directly over chain state via the EVM. And this has a few benefits. The first is that it's faster and more performant. Your transformation logic has direct access to that chain state, so you don't have to go over JSON RPC, which reduces network and JSON serialization and deserialization overhead. And it's also a better developer experience in a lot of cases. Again, you can directly access chain state that you need, and then you can also reuse any code that's actually running on-chain in your off-chain transformation pipelines. So to summarize, a new block gets added to the chain. You execute that block through the EVM with your shadow contract bytecode, which contains all your transformation logic. And then that shadow contract bytecode is also emitting your transformed data as EVM logs. And then, of course, you can send these to whatever data store that you want, Postgres, Snowflake, whatever suits you the best. So this is a perfect use case for Reth XXs. This like co-located ETL process can be really easily modeled using an XX. So that's exactly what we built. We built Shadow Reth, which is an open source implementation of a shadow node built with Reth XXs. And you can run Shadow Reth to generate shadow logs directly within your Reth node. So last December, we launched a hosted platform that allows you to get shadow logs without having to manage your own infrastructure or run your own node. 3 months ago, in May, we released Shadow Reth, which is 100% free and open source for folks who want to self-host and run their own node. Shadow Reth allows anyone to realize the benefits of shadow logs within the comfort of their own node. So why did we build Shadow Reth? We believe that all hosted providers present some trustlessness trade-offs, right? We believe that it's important for anyone to be able to generate these shadow logs in a decentralized way. And one of the reasons why we think this is so important is for verification purposes. So similar to how you could run your own node to verify the data that's being returned to you by Alchemy or Infura or Tenderly, you should be able to run your own shadow node to verify the data that's being returned to you by a hosted shadow fork provider. And the Reth XX framework enabled us to build like a performant shadow node to generate shadow logs without requiring additional off-chain infrastructure or maintaining a heavily modified client fork. So let's dive into how Shadow Reth works. This is what the architecture looks like, and there are 3 main components to Shadow Reth. The first component is the shadow configuration. This is a pretty simple, just JSON configuration. It contains your shadow bytecode and your shadow contracts. The second component is the shadow XX. And like any XXs, you get notified of a new block right when that block happens. So when it gets that block, the shadow XX runs a custom executor that executes the block with the overridden shadow bytecode. And this executor is really just using revum under the hood. It has some shadow-specific modifications that bypasses gas checks. It can also bypass some transaction verification checks to save a bit on performance. And then after the shadow executor re-executes that block, it takes out the shadow logs that were generated in that block and then writes it to a database. And then the third component is our shadow RPC. This was built using Reth RPC extensions that allowed us to really easily add a new custom RPC endpoint that we called shadow get logs. So when you're fetching logs, shadow logs from your own node, you can hit this endpoint and the results of the shadow logs look exactly the same as mainnet logs. And the modularity of Reth and the XX framework was a huge unlock for us to build this like performant shadow node. So huge shout out to the Reth team for all of their work on this. Shadow Reth is already pretty powerful, but there are some missing features and some performance improvements that we think could make Shadow Reth even better. So if you're interested in hacking with Reth XXs or on Shadow Reth directly, we have some ideas for you. I'm not going to go into details of all of these, but come find me afterwards, and happy to chat and give you pointers. Cool. So we are really excited about the progress that we've made in the last few months, but where do we go from here? First, something that we're really excited about is being able to send this data to any data destination of your choice. Being able to generate these shadow logs within your node is great, but there's a lot that you might want to do with this data. So the goal would be to allow you to send this data anywhere you want by simply installing a data connector on your Reth node for your data destination. And lastly, this is just a teaser. I'm not going to go into the full details of how this all works, but we've been working on a decentralized registry of shadow contracts. And these shadow contracts were written by experts, often by the original protocol teams themselves. And these contracts are stored on IPFS and available for anyone to use. And we've been working with some top DeFi protocols like Uniswap, Yearn, Frax, Lyra, Pendle. They've all written shadow versions of their contracts and uploaded them onto this decentralized registry for anyone to use. So with this public registry, you no longer have to handwrite your own shadow contracts, and you can just like opt into pre-written shadow contracts that you're interested in and get the shadow logs for those contracts. As part of this, we've also open sourced a CLI tool that allows you to permissionlessly upload a new shadow contract to IPFS and register it on base, pull down any shadow contracts that were previously uploaded that other people have written and uploaded to their registry. And then you can also use the CLI to really easily generate, like in one command, that shadow Reth configuration file that you can then pull into your own Reth node. And you can find this at logs.xyz. This is just our hosted front end that sits in front of the decentralized registry in IPFS. So with all of this, the vision is you'll be able to permissionlessly opt in to pre-written shadow contracts, run them from the comfort of your own node, and then send that data to any data destination of your choice. We're really excited about this. Go check it out and let us know what you think. And that's it. Any questions?
Thank you for the presentation. That was great. Do you recommend, well, do you think developers should stop writing normal contracts like save gas? Is that going to make a big difference? As more like a vision for the future, I understand you don't have to use shadow logs if you don't want to, but yeah, maybe we should stop writing event contracts and just use shadow logs instead.
Yeah. That's a hot discussion topic. We don't believe that all mainnet logs should be removed from mainnet. We actually think that that's kind of like just removing all mainnet logs is kind of an uninspiring goal. Like it really caps kind of the value that you can bring to the ecosystem. And what we're really more excited about is like the ability to 10x or 100x the data that actually that you can actually capture from on-chain activity. But at the end of the day, you know, developers know best. Developers know what's best for their own protocol, for their own users. Our goal is just to make sure that if developers do choose to omit mainnet logs and use shadow logs, that it is really easy, really cheap, and accessible to actually get these shadow logs.
What happens if the contract that you're trying to get shadow logs from is like behind a proxy or calls another contract that doesn't emit shadow logs or like delegates some behavior?
Yeah, good question. So for proxy contracts, what you're actually shadowing is the implementation contract. So you shadow the implementation, you don't have to touch the proxy, and the proxy will obviously delegate call to the implementation contract, which will then execute your shadow bytecode and emit the logs.
And does that mean you have to have like a mapping of like I'm just looking through your repo and you have like this mapping of the shadow config and you have to like map your implementation as well for proxies?
Yeah, that's right. I think there's a lot we can do better there. Like we can automatically detect when an implementation changes and try to deploy your original shadow contract at the new implementation address. definitely think we can improve that there.
Thanks.
Mm-hmm.
Sorry. Can you explain a little bit about what Pendle did with Shadow and how other DeFi protocols might be like improved with this?
Yeah. So the Pendle use case, if you want to go super, super deep, there is a published case study on, I think it's blog.shadow.xyz, where it talks about kind of all the math and exactly what they're doing. But at a high level, the way that Pendle is architected is they run some off-chain algorithms to optimize the on-chain like transaction route, essentially, kind of similar to how Uniswap generates the optimal kind of pool route path and then submits that to the chain. And they were using Shadow for easily backtesting their algorithm. So they were able to basically backtest and say that, okay, if our algorithm changed with these parameters, if those parameters were actually used for the mainnet transactions, how much gas would the user have saved? And that's kind of what they were doing at a high level. They were doing it for kind of backtesting purposes.
Okay, I think that's it.
Thank you.
Next up, we have Ferran from Flashbots talking about RBuilder, a MEV Builder on Reth.
Hello, everyone. Okay, I'm Ferran. I'm from Flashbots, and I'm gonna be talking about the RBuilder. The RBuilder is the new block building stack that we have developed at Flashbots. So, how many of you know how PBS works? Raise of hands. Not that many. So, this is how PBS works. So this is how block building works. Oh, doesn't point. At the top, you have in green, you have the normal block building workflow. You have the proposer, which will delegate to the execution client the build of the block. So the execution client will use vanilla block building algorithms to return a valid block to be proposed. And here at the bottom is what we call the PBS, or proposer-builder separation. Now we have two more actors. On one side, we have the builder. So builders will build blocks for the slots. And the proposers now will call the MEV boost relay to sort of serve as an impartial auction to select which block is willing to bid higher for that slot. So the MEV boost relay here also adds extra security in case of the proposer not being able, though they might be able at the end, but not being easy for the proposer to like unbundle the block of the builder. So what I'm gonna be focusing on this talk is that actor of there, the builder. So all this stack was introduced, this PBS stack was introduced by Flashbots right after the POS. And we initially open sourced the MEV boost relay implementation, and then we also open source block builder implementation. So this was a fork of Go Ethereum with a more complex merging algorithm. And also all the bindings required to send bits to the MEV boost relay. This sort of open competition got competitive at some point, and more sophisticated players started to enter the block building competition. So you'll have, for example, trading shops with custom order flow that could build more valuable blocks. Most of them will follow the same process. They will take the builder, or they will fork it and add their own changes on top. These are the four main categories that we have seen so far where they have introduced changes. They, as I mentioned before, they have internal order flow that they can leverage, so they modify the builder for that. They may introduce new latency improvements, like connecting to the relay using WebSockets. They can use new bidding strategies to decide how much they want to bid for the block. And to like sort of combine all those three, they build custom merging algorithms. But again, all of them follow the same process. They take the client, they fork it, they add the changes, and they upstream. And I'm not sure how many of you have been in that situation, but that's really complex to do at scale. It creates some sort of psychological fear every time you try to create a new feature, because you don't know if Geth is going to break some interface or what you're doing is going to be available for the next release. Okay, yeah. So we were in the situation as well, and we saw how we were not innovating in block building. And right at that point, we were thinking, okay, how we are going to update our builders? What's going to be our newest strategy for block building? And with the release of Reth, it was easy to think, okay, how we can leverage Reth for that. And the way we can leverage Reth is using its modularity. So it's important to note that Go by itself, by the way Go works, it's a modular language. You can already take code from Go Ethereum and using it as a module. Most people use the AVM inside Go Ethereum. But just because you can use that module doesn't mean that it's going to be easy for you or it's going to be maintainable for you. There has to be some kind of contract in that API for you to safely and in a scalable way to use it. And that's what Reth offers. With the crates of Reth, we are sure, though they can be breaking changes at some point, that they acknowledge that modularity is a first-class citizen of the system. So they are willing to put some API contracts there that they are not going to break those implementations. So following that, that's when we started the RBuilder. So the RBuilder is a modular block builder built on Reth. It's built on Reth. That means that as the common layer uses Reth, Reth primitives, Reth provider, and the alloy types, and that helps us to remove a lot of extra code that we don't have to do anymore on the builder, like typings or encodings. And it's modular in the sense that we want to bring the same innovation that Reth is bringing to the nodes client into block building. We want to make it easier for people to take the RBuilder and create their own sorting algorithms, merging algorithms, add new functionality without having to go through the cycle of forking, merging, upstreaming. Okay. So how is it going so far? Oh, sorry. This is how the RBuilder works right now for the L1 use case. So this is the same picture as before for the PBS example. And now we have the RBuilder that it's connecting with the Reth database to sync all the estate. So to do that, we just use the Reth crates to connect and access that database and get a reference that we can pass to the AVM for the RBuilder. So how is it going so far? As of now, as 2 months ago, we don't run any more Go Ethereum nodes. We just deprecated all the Go platform of the block building, and we only use these RBuilders. They're way more efficient than it was before. And half of them run in this TE platform. So TE is another angle of Flashbots that I won't go into detail, but if you have more questions, come talk to me afterwards. TE is a special type of hardware that is a security enclave where you can run your applications. So half of our builders, and by the end of the day we want to be all the builders, are running already in this TE platform and with negligible performance. We are talking about 5% to 10% loss in performance. Which are the features that I want to highlight? First, as I gave a hint before, is a modular block building. That means that there is a trait that you can implement to add your own custom merging algorithms. You might have new strategies for DAG sorting or some simulation or some heuristics that you can easily plug into the RBuilder, test them out, and send blocks into the L1 chain to see how it looks. Combined with that, we have backtesting. So you can easily check how does your algorithm works, how is improving. You can take a range of blocks from mainnet and see if you are increasing the value that you are generating, also pretty easily. And the third point, and this is something we just open sourced a few weeks ago, we have a local deployment environment. As I showcase here, in order to test the RBuilder, you have to basically run these 3 and sometimes 4 different services. So that was a huge struggle sometimes when we wanted to do local testing or some CI integrations. Now we have a complete local playground. It's on GitHub. It's called Builder Playground. That takes 8 seconds to deploy all that setup, all in memory. Pretty easy to do. So that has helped a lot into testing new features and on the CI integration, and we hope to leverage that to increase more the coverage of the builder. So where are we going from here? These are the 4 major tracks that we are going to be working on for the next months. First one, and that's the one I'm focusing on, we are adding multi-chain support. The same way that Reth can be a node for both mainnet and OP chain, OP stack. We want the RBuilder to also be a builder for L1 chain and also for OP chains. So we are researching how we can make the builder modular to support these use cases. We want to improve block builder architecture, so we want to also research what is the most efficient trait architecture for the builder to support many different block building use cases. Third one, this was mentioned yesterday, is that Reth is not still as efficient as Go Ethereum doing state root calculation. In our benchmarks, we have Geth block builder at 15 milliseconds for hash root calculation, and right now with RBuilder it is 100 milliseconds. So we are merging in the next 2 months a new hash root calculation improvement that brings down the number to 10 milliseconds. And the last one, which I'm the most excited on, we are going to launch a block building competition. So we want to launch like a sort of Kaggle block building competition when people can send their own block building algorithms, train them in some snapshot of training data, and then we'll run them on some test data and create a leaderboard on top of that. So yeah, if anyone wants to try, be on the look for the competition. Yeah, thank you.
Hey, yeah, thank you for the presentation. I have a more general question about how you backtest. I'm curious because I've been talking with friends, or you just said it here, like usually how you backtest is like you take a subset of blocks and you replay them and you see like how performant it was. I'm curious, like it seems very constrained. Like I'm curious if you have other ways to make, like to attest of the quality of your improvements.
So you don't test on a range of blocks. You have to test on the, you have to sort of replay the state at which the block was built, right? So you have to, at point T, you have to start with a state T-1 and all the transaction that the mempool had at point T, right? Because that's the state that the RBuilder used to create the block eventually. Not all those transactions at point T are gonna be end up on the block, right? Yeah. So we have a tool called mempool dumpster, which is also from Flashwatch, which just has, it's like an S3 bucket that holds all the transactions that were in the mempool at different points in time. Right? So if you combine that with an archive node, you can really start to replay a given range of blocks and see how your builder performs. So part of the thing that we're trying to do is sort of ease those requirements to run those backtesting, so you don't have to require an archive node. So we are testing like different strategies there to make it easy for people to run it.
But if you have a different behavior, wouldn't it mean that it would change also the behavior of potential other builders on the network or other actors that would also behave differently if you had a different behavior? which means that your backtesting is valuable in a sense because in this contrived environment you can say, okay, I'm X% better, but it's not like real world testing. So that's why I was just curious if you had like other ways of testing than that.
Yeah, I don't think you will have way to test how your strategy plays out with different block builders. I think this back testing is only to test what's your baseline, on top of which you can start to compete with other builders. But that would be something different.
Thank
you. In your diagram up there, I noticed that RBuilder communicates directly with the Reth database.
Yeah.
Can you elaborate on how the Reth communication itself works and why not just run in process with Reth?
Okay, yeah, that's a great question. So, the way you plug into the database is because of MDX. You can just plug in read mode inside the database. And why we don't make it as a module? We are actively working on that. I think part of the modularity of the RBuilder will be on how you can create different flavors of it, and maybe one of those flavors run it as a module. This current architecture is helpful because the RBuilder does not depend on the chain syncing, right? So you can have the Reth running and syncing the chain, and then you can just restart the RBuilder as many times as you want. While if you have it in the same process and you stop the whole process and then you restart again, you'll have to wait for that chain to restart, even if it's like 10 blocks, right? So by having it separated, we don't combine those life cycles. But I agree that with making it as a module of Reth, it brings like other benefits, like piggybacking a lot of like memory and cache improvements that they might do in the future. So that's something that we are actively researching.
I think that's it. Thank you. Okay, next up we have RalexStokes from the Ethereum Foundation talking about Mev-rs.
Hey everyone, good afternoon, and yeah, this will pair well. It's a very similar take on the previous talk, and let me just try, I don't know how that works. Oh, I probably just broke something. There we go, I guess that'll do. Cool, let's get started. So yeah, you pretty much saw this diagram just in the last talk. One piece that was missing that is actually quite important is MEV boost here. Let's see if, okay. There we go. It's like a big spotlight. But yeah, so you have the CL over here, right? This is driving our view of the consensus of the chain, the execution client. MEV boost is like this like multiplexer component that interfaces between the proposer and the relay. The relay is here, and then the builder's over here. Actually, this is gonna be better now. Yeah, so you can see this whole pipeline, and if you're here, you probably have heard of MEV. This is like a take on the infrastructure, how it looks today. We have this flavor of like off-chain PBS. And these are kind of like the main pieces today. Even in like the last, couple years since the merge, this picture has actually gotten way more complicated. There's like searchers, there's like solvers for different applications, or like various off-chain things with respect to the L1. There's like account abstraction, so then you have like the bundlers there and like all the players in 437 landscape. And yeah. Point being is, if you didn't know, over 95%, it fluctuates, but say over 90%, even up to like 95% of all blocks on Ethereum are built through this pipeline. So it's quite important. And let's see, the next slide. Yeah, so because of, again, how critical it is to the block building process on Ethereum today, it's super important. We want to make sure that there's like a stack of software and like this infra layer is very secure, well tested, and robust. So, as you can probably guess from the picture you just saw, there's like a lot going on, many different actors. They all have to be coordinated in like exactly the right way. And importantly, if there are like security issues at any point in the stack, bugs or things like this, people have a bad day. There's the builder, the relay, the validator, and by extension then users. So like if there's a bug, say, in the relay and they can't release the block, that's like a whole missed slot, we would call it, for the whole chain. And what that looks like for the end user is you have to wait twice as long, let's say, to like have your transaction be confirmed, and that's just very not nice. So what can we do about this? Given its importance and its like centrality to the stack, security is like the top concern. And one sort of, I'm calling it here a security posture, like something that we usually do in Ethereum land is think about implementation diversity or like client diversity. And the way that this whole off-chain PBS with MEV Boost started, Flashbot seeded the system. And it's very exciting that other people have joined to help build it out as well. So this is a talk on Mev-rs, and essentially it's a Rust repo that has implementations of these three key components: the MEV Boost, the relay, and the builder. So what's cool on here? Yeah, I mean, check out the repo. I guess a cool thing for us here, it's like pretty much all in Rust. You'll see there's like a little bit of Nix. That's just like a side hobby I have. I do a lot of like immutable deployments and things with Nix and Nixos, which is super cool, but that's a whole different talk. So yeah, why Mev-rs? So one way to think about it, at least this is where I started working on it, was just as like very much like an experimental toolkit. So it can be useful for like prototyping different ideas or features about like improving or hardening this pipeline, reason about protocol changes. Something we did a few months ago, in the last year at least, was change how like withdrawals should like formally work. Part of this whole process is that you have builders making blocks. They then submit some bid, which is going to be probably different than like the actual value in the block. And this then interacts with the consensus layer. A big thing here is like validator withdrawals. And so something we were seeing is that if you had a payment, let's say, to the proposer, and the proposer also was like withdrawing ETH at the consensus layer in the same block, many of the ways that relays and builders were computing the values to bid would include these withdrawals kind of by accident. Like the withdrawals has nothing to do with like the sort of MEV in the block, so that's kind of just a bug. And having sort of this like playground to experiment with these ideas is really helpful, because then it just provides some way to like ground the thinking around, okay, if we exclude withdrawals, like what does that look like? How does it impact things? Stuff like that. It's also helpful for like hard fork testing, just to have like, again, a full suite of the stack. There's many things like as we go from like, okay, all the EIPs we're thinking about to actually like deploying them in sort of mainnet, there's like a huge process to like get to that final endpoint. And a big part of this is like testing all the pieces together, interactions between various EIPs. And then, as we do change the protocol, there are like direct impacts on this builder API, which is, again, this interface. Maybe I'll just go back really quickly. This interface, I broke it. Interface here between the validator and the consensus node and MEV Boost itself. There's like a specification of how this should work, and basically anything we do over here that changes how the chain looks is going to impact this component, and vice versa. Another thing to note is there's like quite a bit of other Rust software that I have that's, again, sort of focused on the consensus layer and things there. So like one thing to point out is a lot of Mev-rs uses these two dependencies. I have a repo Ethereum-consensus, also SSZRS. So Ethereum consensus is essentially an implementation of like the consensus specs in Rust, and similarly useful for like prototyping and like reasoning about different features of the protocol. There's also an SSZ library that's like a serialization format that has like a Merkleization scheme built in. It's sort of the core primitive when thinking about any consensus data type. So helpful for all of those reasons. Another thing was to directly address this lack of implementation diversity. So like kind of as I was pointing to a minute ago, especially like in the earlier days, there was sort of just some initial implementations, at least that were open source by Flashbots, and otherwise there wasn't anything out there, at least that was open source. So the Flashbots implementations were in Go. I like Rust a lot more, as many of you probably do. And it was like a natural choice to be like, okay, yeah, we can kind of like kill two birds with one stone by having like a nice Rust stack. Rust has this tagline like performance, reliability, productivity, pick 3, and you can clearly see how that plays very nicely with something like, again, securing this very critical part of the protocol today. That being said, the community has grown a lot, even since I started like working on all this stuff. The ultrasound relay project has like stepped up and been doing a lot of development like their relay. You can go to the repo there, and you can see a lot of open source, also Rust software they have around different parts of the stack. And we just saw this talk on RBuilder, which is a fairly new effort by Flashbots to do take a similar view with respect to the builder. And importantly, open source. Like this was another key point, was that because of the way MEV works, right? It's like if you have some like edge or some alpha against your competitors, you're very incentivized to like not talk about it, right? What that means then is like if you're a more sophisticated actor, because say you're like a hedge fund that can like afford really, let's say expensive devs, it's really hard then for new entrants to come in and enter into the fray. So the issue there then is like barriers to entry around this process. And yeah, open source is good. You could imagine that it would help the sort of market structure. I mean, another key point here is there's essentially only 3 top builders, which is like an incredibly small number. And that's bad for other reasons that we don't have to get into now. But basically, the way to think about this is the more the merrier. And one way to start to address like the market composition is just by reducing barriers to entry. So let's just walk through some of the components. This is just like a screen cap off GitHub. And yeah, basically, there's, again, a MEV Boost implementation, which is this multiplexer I'll get into in a minute, a builder, and a relay. There's this like Mev-rs library, which is kind of just like a catch-all for various like common utilities and things like that. And then there's a binary to like run it all, tie it all together. So we're going to look at each of these 3 in turn, but essentially, yeah, they all are like ready to support Deneb, which is the latest hard fork we have on Ethereum. There is some early work on Electra. So let's look at these pieces now. So the first one is MEV Boost. And yeah, essentially how it works is you go to like buy a block from a builder, and what that ends up looking like is you talk to these relays. You can generally be connected to like many relays, and then you get bids when you go to like sort of sell your block space as a proposer. You need to pick presumably the one that pays you the most. And then what that looks like is you get say a set of 3, 4 bids. You need to pick the highest value one. So MEV Boost is just this component. It's pretty lightweight and essentially just performs this like selection process for you. And yeah, like it actually, like if you look, it's really not much code. The core thing is really just like getting the bids at the right time and picking the most valuable one. Okay, so next the builder. You'll probably see a lot of overlap with the RBuilder here. I mean, I think there are a few different design decisions that we've taken so far, but generally, a builder with Reth. And yeah, so let's take a look. I guess one sort of, I think from what I understand so far, like the biggest difference is actually, so this builder is as a node extension to Reth. It just builds on top of Reth as this like very modular, almost collection of libraries, and just sort of extends the execution node in a way to do like the sort of MEV Boost parts that a builder needs to do. So the key thing is leaning on this payload builder abstraction. That's super awesome. Shout out to the Reth team for that. And the payload builder is tasked with like actually crafting the blocks. Right now the builder just uses transactions in the mempool. So you like look at the mempool and just build a block from what you have there at the time you need to. There's this component, this notion of like an auctioneer, which is doing a lot of the like organization and like coordination around all the different timings and like when to build blocks, when to submit blocks, and things like that. There's also a bidder component that then, like, the idea at least is that you'd have this bidder that you could like write your own custom bidder. And how it would work is like whenever there's a block made by the payload builder, the bidder would see this, say like you would see, okay, I built a block for like 1 ETH, and then the question is now, okay, when, sort of how much value do I want to keep versus give to the proposer, and when do I want to make that bid? And how this kind of works is, let's say there's a new slot and now a new proposer is going to make a block. You could like have many payloads. Like this really should be like a continuous process. And then you can in turn imagine this bidder is also this like dynamic, very continuous thing as well. The bidder then can in turn, for example, look at the different relays that it's aware of, and then you see like sort of different competitive strategies between different builders, because I can actually see what other builders are bidding in real time, and then use that to inform my own strategies. So yeah, this might be a little hard to read, but going to do a bit of a code walk through the builder and just kind of demonstrate how it extends Reth. So the place to start is this payload service builder, which essentially ends up building a payload service. And this is the piece of Reth that handles block construction, like within the EL. And you know, it does this stuff. I think there's also great examples in the Reth repo itself around how to do things like this. Ultimately, you end up with right. So this is essentially like the abstraction that you can sort of implement to customize this behavior. And it does a bunch of stuff, but you can't see that. OK, sorry. Ultimately, there's a custom payload builder that this repo has that sort of, yeah, it's the place to implement all the different like logic you would need for the MEV-boost auction itself, which I'll touch on in a minute. Importantly, like for example, there's a signer that's passed in, because there's a way that you need to like pay the proposer in like a particular format. So then the builder then has like a balance they're aware of, and then a way to make transactions to pay the proposer out of that balance. There's a fee recipient for the builder. So like again, if you had a searcher submit a bundle, there's a way to like say, hey, this is how you should pay the builder. Yeah, you can't probably, yeah, you definitely can't see that down there. I'm sorry. But there's also a reference to like the bidder that gets passed in. OK, this should be better. So, right, the payload service builder is the thing we're just looking at, and then ultimately it gets passed into this node builder type, which if you've extended Reth at all, this is like a pretty, yeah, you should be familiar with this. Basically, there's a way to like take the default execution client that Reth provides and customize it, and there's like different, I mean, it's actually very flexible. But you can have like different nodes, or sorry, different types, and then different components in the thing. And in this case, we just want to customize the builder component with the payload builder. And then otherwise, there's a way to like sort of asynchronously launch the other components, like the auctioneer and bidder, to tie everything together. And yeah, I was just going to highlight that this is, again, the other side of this channel to reference from the bidder to the payload builder. The code is like a little split, and I could just kind of put these screenshots. So again, if you're curious, I can show you after a bit more of the structure in the code itself. But ultimately, you can imagine setting up the payload builder with the Reth extension, and then going to this part, where then you wire these other components together. Again, having a reference to the payload builder, the bidder, and yeah, there's a bid channel there. So that's a flavor for how some of the code looks, just to like actually extend Reth. Let's walk through like high level how this works. Like the first thing this is driven by is a fork choice updated notification from Reth. So the way that you run nodes on Ethereum today is you have a consensus node and execution node. And so when there's essentially a new block and it's part of the consensus node knows this. It tells Reth, which Reth then needs to update its head. And the way this is customized is then this notification gets dispatched to these various components within the Mev-rs builder. When you see you have a new head, you now need to figure out if you need to build or not. And there's information in the fork choice along with some other information you get from, say, your consensus node to know who the proposer is, and then more importantly, if it's registered with different relays that you're connected to. So you do that. If so, there's also like some preferences that validators have when they register. For example, like their gas limit that they would prefer for the block, and then also the fee recipient, which is how they should be paid. And if you find some of these, you start building. If not, you can just ignore this particular update and just wait for the next one, say 12 seconds later. So if you do need to build, then for each proposer, because actually you could have multiple proposers, just given the way the consensus works, then you want to start building payloads. This is where like the core Reth machinery kicks in. You pass in this metadata around what the proposer wants the block to look like, and essentially for every block that the payload service builds, it's sent to this bidder. The bidder, in this way I was talking about a second ago, says okay for a given bid, how much do I actually want to pay out, when should I submit the bid, and it does all that. The bidder then sends the notification to the builder again at the right time to say, hey, go ahead and finalize this payload with this, say, this value, this payment. And then that ends up getting back to this auctioneer component that then sort of puts the block in the right format and submits it via the right APIs to each relay. So the cool thing here is it's built on Reth. It's fast. I don't have benchmarks, unfortunately, but I've been using it in various like devnets and testnets, and it works. I think I know from the experiments I've done that there can be quite a dependence on hardware, but assuming you can toss enough hardware at the issue, it can actually handle quite a number of different like auctions in parallel. And you've heard this many times now, so it won't be a surprise, but the biggest bottleneck that you quickly run into is just computing the state root for the final block. It's a quite heavy computation, and there were talks yesterday, if not also today, around this problem in Reth. Quick shout out again to the Reth team. They've been super helpful around like iterating with APIs, just answering questions and being available, and also just very open to like feature requests and things. Something that might not be clear, but is definitely part of this problem domain is that you might actually want to like very iteratively build the block in terms of even just like the APIs. So rather than saying, hey, Reth, go build a block, you say, go build enough of a block that I can see how much MEV is in it. And then I want to turn around and say, like, bid this much, right? Because that also needs to be a payment transaction in the block itself. So there's things like this where you can imagine extending or hardening like these Reth APIs. And yeah, the Reth team has been super helpful, helping me understand and also just responding to requests like this. To keep the shadow going, yeah, all of this is built on top of Reth. This would not be possible without an execution client. And in particular, the fact that Reth is so extensible and modular, it makes this like super nice and easy. It also uses Alloy in a few places. Like in particular, I used Alloy Signer just because I needed a way to sign transactions, and it seemed like a really simple, nice crate to do that. I've even used Foundry more for just like making ephemeral wallets on these different testnets and things, and using that to like fund the builder, move funds around, stuff like that. So, nice work. Okay, we'll touch on the relay. This is like the last big piece, and the relay component, it kind of sits in between the builder and the proposer. And the idea is builders are like basically spamming relays with blocks. They have to figure out which blocks are valid, which conform to like the MEV boost auction rules. For those blocks, they then can expose them to the proposer via these builder APIs. Just as of today, I would say this is the least sort of developed part of the whole suite in Mev-rs. The way that it works now is there's essentially this like trusted builder idea where essentially it only takes block submissions from hard-coded builder pub keys. And this is basically just because I don't have to then think about implementing block validation. So in short, it means built with the MEV builders. A key piece here is like payload validation in terms of like hardening this out into like something that looks like more like the production relays we see today. And like the Reth node extension strategy went so well with the builder, I really want to do this with the relay. And a few months ago. That's probably changed. So if you're interested to contribute, that would be a place to start. And yeah, status, it works, super awesome. Here's a tweet. There's like 2 blocks from Sepolia, and yeah, it's super cool. So that's it. There we go. DMs are open. Here's my Twitter page. And yeah, I would love contributions. I try to mark like good first issues. It's tricky sometimes because like the Reth APIs are, they've gotten more stable in the last couple of months, but like they were also changing as I was building some of this. The foundations in terms of how I think like the builder or the relay should be structured in this repo were also changing. But yeah, if you're interested, please reach out and we'll try to find a nice way to contribute. And otherwise, I'll take questions. Thanks.
Hey, great stuff. So you touched on this near the end. Looking at it from the perspective of a proposer, it is kind of scary to be signing a block where you don't know what's in it, right? if it's an invalid block or something, you're out your slot. And that's bad for everybody. What do you see as ways to incentivize building new relays, or like what's in your view and the broader view right now more long-term solutions for that issue?
Yeah, this is tricky, and like I think a lot of the pain point, like I think there's many ways I tried to like address this. This was one way. It was just like even say a year or two ago, just be like, hey, actually have like nice software that people could use. And yeah, like what you're really getting at is the fact that these are all public goods, at least like the relay in particular, and like more of the consensus software with MEV and things like that. And funding public goods is very hard. If you have a nice silver bullet, many people in this room would love to hear it. Yeah, there's like various efforts around like making some sort of DAO-like structure for relays, and that's one way to fund them. Otherwise, yeah, generally how the relays work today is like they don't have like any profit. Like they essentially operate at cost, or they're just operating out of pocket. And yeah, it's tricky because if you were to have like a for-profit relay, then you essentially be outcompeted by the other relays that wouldn't charge, right? But at the same time, you could imagine like value-add services around a relay, and there's like a whole bucket of things around like customizing the actual type of the block. So like you could say as a proposer, I want to do like, you know, maybe I want a block that, I don't know, well, there's many things you could imagine, but there's things around customizing the actual contents of the block that the relay is positioned to like implement, and this could be something they add. I guess, yeah, to give you one example, you could imagine something almost like pre-confirmations or things like this, where it's like not just the contents of the block, but like extra semantics on top, where, you know, you could imagine a relay doing this, and this is now something that they could actually charge for in like a sustainable way.
What do you think of the people are usually taking relays for granted because relays is usually like one single point where people trust in Ethereum ecosystem, like especially like for like pre-confs and stuff like that. Like people are proposing protocol at which you like delegate like block selling on the relay or stuff like that. Like what do you think of this evolves of, you know, research?
With pre-confs in particular, or
anything in general, just people taking relay security for granted, thinking that like they run on TAE or whatever.
Sure. I mean, I don't know if people take it for, okay, they do take it for granted until for some reason, you know, let's say they're like a solo staker, they have a few proposals a year, and suddenly they wake up one morning and they thought they had a block land, but it, you know, the relay failed for some reason, and they found out they missed their proposal. Like this happens to people, naturally they become very upset. So, yeah, it's a thing where people don't realize it's an issue until it happens to them, which is not good. And yeah, I guess more on like the pre-comps point, like again, generally I support experimentation as long as it's sort of, you know, safe in the right way. So yeah, I think we could see a lot of things evolve around like things that improve UX, or again, like features around like how blocks are built in Ethereum that are valuable to people. And yeah, maybe you could start to address some of these sustainability issues.
Looks like that's it. Thank you, Alex.
Thank you.
Okay, next up we have Ludwig and Will from Sorella talking about Brontes, how chasing MEV led to a general purpose blockchain analytics engine.
Hey, chat. Today we're going to be presenting Brontes, which is basically the endeavor of us chasing systematic MEV detection, and in doing so realizing that we ended up building somewhat of a general purpose blockchain analytics engine for Ethereum and all like layer 2s that are based on the EVM. So why Brontes? We're not masochists. We have dealt with trace data in the past. Classifying it, pre-processing it, normalizing it is just absolutely painful. And personally, we don't really like that step as opposed to the interesting analysis that we far prefer, like focus our time on. And so Brontes really, the main initiative is to reduce all of that work, ensure and streamline the entire pre-processing portion of the work so that you can jump immediately into the analysis portion without having to worry about how to decode Curve's 56th pool implementation, or how to implement discovery for a factory that produces 15 different contracts at a time. All of that have been such a significant bottleneck, and this was really aimed to completely mitigate that. The other thing is that we're working on MEV, we're working on minimizing it, and although everyone and their mothers love to chat about MEV, unfortunately we don't have that good data today. There's great research on the validator payout side, there's great research on the timing game side, but in terms of data on systematically identifying actual MEV transactions and providing accurate kind of P&L statistics, we haven't seen that much. And on top of that, there isn't really an open source place where we can all kind of participate and contribute to the discussion on how we want to classify, how we want to improve the taxonomy. So what you end up needing to be able to do this is basically akin to a feature-complete block explorer with extra steps. This is something we didn't necessarily realize in the beginning, but we kind of pushed through painfully. So you need to be able to decode and classify these complex DeFi interactions. But the very important thing here is that you have to normalize them so that you can operate on a unified type, so that when a Uniswap swap or a curve swap happens, you don't have drastic different data representations. The other thing is that you don't want to lose the context that you gain from operating at the trace level. Because when you're operating there, you have the call frame hierarchy, and then you can use that to infer many different things. So in this normalization and classification step, we really wanted to maintain that level of context. Then the second thing is that you're going to need a lot of off-chain data for this. So you need an efficient way to store it, an efficient way to read and write to it. One more complicated thing is you need prices for almost every single token, and you need them at a transaction level granularity. Because if you're looking to accurately price a sandwich, if you're looking to accurately price an atomic arbitrage, you can't depend on CoinGecko's API. And trust me, we initially tried, their rate limiting is also just not conducive to how blazingly fast Brontes is. And then the last thing is you need extensive metadata on addresses, on contracts, also just more simply on builders and searchers, because you can't really accurately compute the P&L because the interactions in a lot of these searchers, between the searchers and builders, are quite complex and are not straightforward, where you'd basically mark out a bundle as negative in P&L if you didn't know about the special deal that the builder and the top searcher had, or the fact that Manta Builder, which was Jane Street, or another unknown builder by the name of Beaver, would actually send all of their profit directly to the builder, so the searchers would look unprofitable. You need that global context, because otherwise you just can't have accurate numbers. There we go. And so putting all of that together at the high level, you can think of the pipeline as, we have a block, we're going to trace it, we're going to build the tree where we do the classification and normalization, and at the same time we're going to fetch the metadata. And then after all of that, we've collected the necessary data for our analysis, and we can operate our inspectors. So to collect and normalize actions, basically what we use is a custom Reth tracer that matches logs with the call frames, and then a macro system that provides a really clean interface. We'll tell you all more about it.
All right, so to start, what we basically do is we collect all the traces in the transaction tree, or in the block, of course. And then we for each call frame, for each transaction, we go through a process. Go to the next one.
Yeah, I'm going to try and point out. So yeah, so here you have the individual transactions, and then they get processed at that point here.
Yeah, right here. So if it's a call, it goes over to our protocol classifiers that will be on the next slide. And if it's a discovery, it goes over to the discovery classifiers. This also will trigger a pricing update, which then says, hey, this call frame used, well, if this is an ERC20, we need pricing at this exact transaction index in the block. All right, go to the next one. All right, I think we can skip this one.
Yes, so this is very similar. Basically, the protocol classifier is just a dispatch that you do on an address that is labeled as being part of a specific contract or / protocol. So for example, Uniswap v3 would be labeled as Uniswap v3 protocol, and then we'd have the function call as the additional portion of the match key that enables us to match against the specific function and then decode and then classify the data.
Yeah, so for this, we built a macro. The goal of the macro was just to simply abstract away and give just a really clean interface for dealing with all of these unclassified types and call data. It's kind of very messy in the back end if you, for every single one, are doing all this decoding manually. So we thought it'd be nice and clean to put it in this. So basically, all you have to define is the path to the protocol module, the path to the alloy function, call type, log type, and what you want your closure that actually does the logic behind it to be passed in. So here, there we go. Okay. So here's what a Uniswap v3 mint call looks like. Oh, keep breaking it.
All right.
All right, there we go. Yeah, so you can see here protocol, and then the mint call, that's just the first two entries are basically how we create the key that people match on, the action type, the log that you want, and for here, we just want everything. So with that, you can see, I mean, it's probably 12 lines of code right here, just reading from the database to grab protocol info, take the deltas, return the mint. It's really that simple for pretty much all protocols, except Curve. And then on the flip side, we have the discovery. So it's another macro, surprise. We have the create pair call and then just the factory address. And I mean, this is even more simpler, right? It's just take the two tokens, name the protocol, insert into the database, and for almost all of the discovery impulses we have out here, it's this clean, which is really nice. And it's super simple to test as well.
And the nice thing is, so as soon as a create pool is effectively discovered, that gets stored in the database, and then any time that there's a function call to that contract, we'll then run the action dispatch, which will classify the underlying swap or mint or burn or whatever interaction. So this is really like an extremely zoomed out overview because it would take an hour to present fully on this, but I think this is probably the most complex portion of the entire project. So basically the main problem is that you can't afford to load all of the state of all of the pools if you want to be as comprehensive as we were trying to be. And you need to find a solid enough proxy to be able to identify what the optimal route is so you can mark out an instantaneous price at that specific transactions index in the block. So what we did to simplify, and again, not perfect and very much room for improvement, is we use a global token graph with like the connecting pools as edges for the token nodes. And we use that connectivity as a proxy for liquidity, which enables us to build subgraphs that are more focused where we can actually afford to load all of the state for each pool and then compute the optimal route and then identify the instantaneous price. And so we're able to price basically any token that is on Uniswap, V2, V3, swap. We started implementing Curve. We have, we don't have the willpower for that. So if anyone wants to take that on, that would be great. Thank you. Yeah, and then the separate portion of the data that you're actually provided is the block metadata. And this is a really valuable portion where you store all of the data that we could possibly think of could be useful in the analysis of any financial interaction. So you have the relay data, the builders, the bids, the fee recipients, the builder metadata with connected searchers. So what searcher addresses are vertically integrated with Beaver, what searcher addresses are vertically integrated with rsync, basically any form of metadata that you could think of on the builders, even their IP locations, but we're not sharing that. And then you have the address metadata, so labels from various providers. Then you have the labeling from private transactions. Huge shout out to Chainbound for that. Thank you. You guys did an amazing job and made it super easy for us. And then you have the propagation time for the blocks. And the biggest portion of the data are all of the trades and quotes for 95% of the pairs across the top 5 crypto exchanges. So to inspect a block, now that we have all of this data, now that we have this classified block, we can move to the interesting part where we provide the block tree and block metadata that I mentioned right before, and we pass it into the individual inspectors that all run in parallel. And so those individual inspectors then produce their results, and there's a final processing step where we can compute the final block P&L and also deduplicate the results. And this is one of the surprises that we had while building this, is that if you miss out on the deduplication and filtering step, you're not going to be able to label things accurately, because the MEV can look exactly like another type of MEV if you're not able to filter it out. So say an atomic arbitrage in a SEX-DEX trade, the atomic arbitrage is obviously getting an advantageous rate. If you aren't able to identify that as an atomic arbitrage and only run, say, a SEX-DEX inspector, well, then now you're labeling it as SEX-DEX. So that is like super important to deduplicate. And the funner part in the processing is actually the composition, where you can take a JIT attack and then realize that it's actually JIT SEX-DEX. Or you can take a JIT and a sandwich and realize that those are actually the same bundle. And so then you can kind of compose these simpler MEV types into complex types.
All right, so we started off with this whole thing as MEV, 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 but then we realized, as Ludwig mentioned in the start, that it kind of is applicable to anything. So like if you wanted to build an inspector that just did something super simple, this is all you need to implement, right? It's just you define what block window you want to look at, what you're going to return as a result, and then just write your code, right? So next slide. Oh, no picture again. Oh, there we go. All right, so, and then at the higher level, right, we have these things called processors, which is just a collection of inspectors processing that generate the same result. So all you need to do is implement your process result function and then create your config, right? And you pretty much can do whatever inspecting you want, any analysis that you want. All of the complicated actions are just all hidden away. So it's super easy to build whatever your mind can think of, really.
And quickly to touch upon like the block window portion. So that's a feature we actually very recently added. But to explain, this basically enables you to say, okay, I want 5 blocks in a row directly provided as data. And so this is something that we haven't used that extensively in the code base yet, but is super useful if you're trying to build, say, EV intent inspectors that look across multiple blocks and see transactions in previous blocks that are signal for a statistical sandwicher that is going to look at approvals on token contracts to then front-run transactions. And finally, it's blazingly fast, at least kind of. Again, we don't have benchmarks, but it runs in two main modes. It runs historical ranges, which are broken up into chunks, and then those individual range executors will all run in parallel. And then at the same time, we have a tip inspector that is specialized to follow the tip of the chain. Then in terms of future works, we'd really love to see support for L2s. You don't have to do that much. For OP Reth, for example, you have to do a tiny bit of a refactor on the discovery and just update the address book to match the latest chain. Then we'd love to improve the MEV inspector methodologies. Sexdex is always going to be an estimation, but the closer we can get to that, the better. And also in terms of long tail MEV inspection analysis, it's very hard to filter out a lot of false positives, but with a decent amount of work, I think we could get something really compelling. And then EV intent inspectors are really high on our roadmap. Cross-chain MEV inspectors, although I'm still strongly of the belief that this is shared sequencer PSYOPs, but I'd love to be proven wrong. One other kind of very off-topic feature that we'd really love to see is a taxes feature with Brontes, because you have all the transactions, you have an ability to decode them, you have all of the prices, and you know when an address traded. So it wouldn't be too hard to actually be able to give you a almost perfect report of all of your on-chain trades. Although the actual legal calculation of how much you want to pay is probably not that simple, but moving over that. And then improving the speed and reliability of the DEX pricing and extending it to support more protocols would be really amazing.
Yeah, so just a shout out to everyone over this past probably 8-9 months of just constant work on Brontes. I mean, Joe especially.
Yeah.
Yeah, he went through a lot.
Yeah, had to implement hundreds of bespoke connections to all of the varying centralized exchange streams. So huge shout out to him, because otherwise this wouldn't have been possible. Then in terms of resources, you can scan here. There's the GitHub and then the book. Leaving it up. Oh yeah, quick acknowledgements before I'm done. Sorry. So huge shout out to the Reth team and the Alloy team for building the primitives that made this possible. Special mention to Danny Popes, because we initially tried to use the sol macro on every single verified contract on Etherscan, and I can tell you we found a few edge cases, like what was the keyword for Rust in the contract. A bunch of ridiculous stuff, and he patched up all of that, so huge thanks. And then big thank you to Gaussian Process and Kevin for reviewing our inspector methodology and kind of going through the results. So huge thanks there as well. Contact us here, and we're also hiring for Rust devs. There we go. But yeah, that's it for us. Thank you so much. Oh, and this is a quick sneak peek at the front-end website that we're going to be spinning up very soon.
Any questions for Ludwig and
Shit,
Will?
I forgot the questions. That's right.
Yeah, thanks guys. Great presentation. I'm actually curious about how do you get the metadata regarding the private order flow? Like you said, okay, we have metadata about the searchers and the builders and their private deals and etc. Considering they're private, how do you get the information regarding that?
There's a media trained answer, and then there's the real answer. The media trained answer is that we are on-chain sleuths and do extreme data analysis. The real answer is that you can contact all of the competitors and get them to snitch on each other, because it is in their incentive to give you information on how their competitor is operating. So that has been an extremely fruitful source of information.
Yeah, thanks. Looks super cool, and I'm excited to see this dashboard that you just had go live. So given all of this, the rich software you have for the analysis of things and all the analysis that you've done with it, like what's one surprising thing that has come out of this?
So there are a few. There are a few. Sexdex is not as competitive as people think. Builders are, on paper, clean, not sandwiching. But if you mark out a lot of the sandwiches, they don't appear profitable. And that is for a simple reason that they are working together. So they are shifting the responsibility on another party. The other thing is people love to make fun of, well, at least in the very niche MEV research community, people love to make fun of just-in-time liquidity attacks. Because everyone says, oh yeah, they're not profitable, you're basically always better off sandwiching, which is almost certainly true. But when you mark out JIT attacks, they are 99% of the time unprofitable until you mark them out against a centralized exchange and you realize that this is not a just-in-time liquidity attack that is trying to steal the fee from a liquidity provider, but rather this is a Sexdex arbitrager that is also a builder that happens to realize that you're trying to trade at a discrepant price, but that price discrepancy is within the fee bound. So they don't profit from arbitraging, but from trading against the pool directly because they pay the fee. But where they do profit is if they provide the liquidity, they get paid the fee, and they get to clear you at this discrepant price and have effectively swapped. But that was like a really interesting kind of point that we came to understand, because you would expect Sexdex to really be bad for LPs. And everyone says, oh, Sexdex is great for the chain in terms of getting prices in line. But it turns out when your builder is also a Sexdex arbitrager, you as a swapper are also getting a pretty bad deal.
What do you see as the most prevalent forms of MEV after this analysis?
There's a lot of atomic arbitrage that we've seen, but mostly Sexdex. There's Sexdex almost every block.
Yeah, it's Sexdex, and I'd call it sandwiching, but it's really just Jared's trades at this point.
Yeah.
It is insane how much this guy trades. He's the top 3 counterparties on Uniswap are Wintermute, Beaver, and Jared.
Cool. Really cool code base. I'm excited to take a dive in and see what's under the hood. One of the questions I had was if you could elaborate a little more on the block inspector process and how you actually create this sort of compound classification between different strategies like JIT and then Sexdex as well. Like what is the actual control flow that's being able to classify this compound behavior?
We kind of glossed over this a bit, but we have this tree that is just the hierarchical structure of all of these normalized and unnormalized actions. So then with these inspectors, you more or less just get passed in this tree and a bunch of metadata pricing. So with that, for example, with like a sandwich, we just go through all of the traces, mark out the same addresses, take those addresses, take those possible victims, and then look at the pool overlap, say, oh, this is trading on this pool in this direction, victims in this direction, backrun in that direction. You got a sandwich.
And you have nice utils where on the tree you can say collect, and then you pass the action type. So it's like collect swaps. And this will give you all transactions where a swap action has happened. And then you can also collect these specific actions out from each transaction. In terms of the composition aspect, that happens really at the last stage once all individual inspectors have run. You have 2 things. You have the filtering / deduplication, and then you have the composition step. The filtering says if there is a type of this type of MEV and this type of MEV, give priority to the one that you decide. So this is useful, for example, atomic arbitrage versus Sexdex, because atomic arbitrage will be stricter in terms of what we can classify it as. but a sexdex will look like a positive P&L. And then for the composition step, again, it's just the results from the JIT inspector, for example, and the sandwich inspector, which will naturally overlap if it's a JIT sandwich. And then you can declare a specific composition function, which takes these two individual bundles, at least as they're built, but are actually the same bundles, and then unifies them into a single complex MEV type.
Okay, we have time for one more question.
Now that you have all of this data and you've like kind of had time to process it, maybe how does it affect your outlook on like the designs like that the Ethereum research community is looking at as far as like proposer builder separation or any of these other ideas, like what you would recommend or urge people to do? Because you mentioned like people wanting to talk about it, of course, but like what actions or things are you guys kind of like thinking of after doing this analysis?
I'd say like two things. Now we have the data. I don't think like having this data is enough for us to kind of have a super opinionated view on what is right and what is wrong in terms of the PBS roadmap, given that there's so many second order effects of possible solutions that we might imagine. So that's why like I try and be very careful on like giving like very specific kind of guidelines there. But that's also a very boring answer and doesn't tell you anything. So the second portion, and disclaimer, I'm very much talking my bag here because this is what we're working on. But what we saw is that this idea that there's so much like general MEV is kind of psyops in the numbers. 99.9% of it is just all the same. Like even liquidations don't matter that much. It's really just sandwiching, atomic arbitrage, sexdex, in no particular order, by the way. And from that, like we know that applications that are being designed today have, or at least claim to have, immediate solutions towards it. So if anything, I'd like to see less of a focus on handling the redistribution and prevention of extraction at the base layer, because I think that very quickly becomes quite opinionated, and rather push it to the application layer. But that has like significant kind of trade-offs. One of them for kind of applications that control their sequencing, and the other is just complexity. If you're an app dev, and now you're building on a financial primitive that is known to generate and produce large amounts of MEV, you now have to handle that yourself and be a big boy about it. And that is not easy. So yeah, like a lot of trade-offs.
Thanks, guys. Okay, before we move into the hacking portion of the day, we have a couple quick announcements. First, we're going to have Andrew from the Cursive team, who's been powering your really awesome NFC badge experience, share a bit more.
All right, hope all of you enjoyed tapping your badges, and thanks for trying it out. If you're curious about any of the cryptography or MPC stuff, feel free to come find me and ask any questions. Two quick things. Number one, you've been collecting flowers for every single person that you've tapped. Every single person has a unique flower. So you can go in the app and tap your own badge, and you can see a garden of all the flowers you've collected. It's pretty neat. It's pretty cute. We're going to share our flowers to Twitter, so if you want to do that, feel free. And the second thing is you can make a proof that you've met 50 people at the event, and or Vivek, we will give you one of these exclusive NFC rings. So very special. And thanks so much.
All right, so